Okay, now it should be running.
Sure. Now it should be running. Oh, can you? Yeah, okay, I can hear it myself. Yeah. All right. Good. So some technical issues, but getting there. So let's see. Let me share screen again. And let's just have my intro slides. What time is it?
Dorsa, before you do that, quick question. Can you in the YouTube chat see where I posted the Slack link, or is Google removing the links?
Sure. So on the Slack, you'll find the research groups and our sponsors.
It's just above that. Meanwhile, feel free to.
No, it's not showing it. I thought like the above that is me saying some technical difficulties. Actually,
I'm posting the Slack
link to the web page we're controlling, because apparently YouTube is censoring my URLs.
Okay. So.
Or maybe potentially Dorsa, maybe because you're the admin, if you paste it in there, maybe that goes through.
I think Erdem is admin too. I think he created it. So
I pasted it in the Zoom chat. If one of you guys can just paste that in the YouTube, that would be good.
Okay. Erdem, can you do it? All right. Shall we start? We are getting there. Any objections? Okay, everyone's here. Great. Okay, so let's start. Hi, everyone. I'm Dorsa Sadigh, and welcome to the Bay Area Robotics Symposium 2020. And yeah, welcome you guys. And in general, this year was kind of crazy, right? We had the COVID and we had the fires, and based on all of that, we decided to go virtually. This year was the Bay Area Robotics Symposium was supposed to be at Stanford, but we were doing it as a virtual event. And in future years, we are going to switch between Stanford and Berkeley like usual. So all the information is going to be on our website. So it's bars2020.github.io. So feel free to check that out. Slack link should go on there soon. So if you want to get on our Slack channel, you can find that there. If you have any questions or anything, feel free to put it on the YouTube channel under the comments. We'll monitor that. And yeah, let's go with that. So this is our schedule for today. It is pretty compact. We just try to put everything in half a day. Usually bars is a full day, but we try to put everything from now, 8 a.m. until 1:15. So let me tell you when the breaks are, because that's probably important. So 9:30 to 10, we have a break, and that is kind of analogous to our poster session. So that is when students are going to be on Slack. And if you want to go ask about spotlights or go and chat with different students, different groups, different companies, that is a good time to do that. 12 to 12:15, we have a lunch break. It's a very short lunch break. I understand that, but we're again trying to put everything in half a day. And then after 1:15, the event ends, but the Slack is still going to be up. So if you want to talk to students, if you want to message people, chat, feel free to do that over Slack. I think Slack is going to be up for the next couple of days and so on. All right, so what else is on this schedule? So we're going to have faculty talks. We have 3 sets of faculty talks. So 8 to 9, we have the first set, which is 7 faculty talks. Each of them are 5 minutes. Then the second set of faculty talks is 10 to 11. And then the last set of faculty talks is only 6 faculty, and it is 12:15 to 1:15. This is the list of faculty who are giving talks in each one of these sessions. Please find your names, and if anything looks weird to you, let us know. If this is not the order you were expecting, let us know. All right, so in addition to faculty talks, you're going to have student spotlight talks too. So that's half an hour, 9 to 9:30, and 11 to 11:30. And these are pre-recorded talks. These are 1 minute. We have 2 students per group, and they give 1 minute talks. And they also have their talks over Slack. They have posters, they have slides over Slack. So as you watch these talks, if you're interested in any of them, feel free to go over Slack, talk to students. In addition to all of these, we're going to have a keynote. So we're really excited to have Rodney Brooks today with us. And he's going to talk about robotics research methodologies aimed at startups rather than academia. And that is really exciting. And that's going to be at 11:30 to noon. So that is the full schedule. A few other logistic things that I wanted to mention before we start. So all talks are streamed online. So if you go on our website, you'll find the link. You can go there and you can basically watch the talks. It is 10 seconds delayed, so be aware of that. How do you ask questions? So if you have questions about any of the faculty talks or basically anything, feel free to just put it under comments here. And that is the way for us to monitor your questions. And again, remember, everything is 10 seconds delayed. So if you have questions about faculty talks, feel free to put those questions up before the end of the talk. That's perfectly fine. Okay. All right. So in addition to that, faculty, you are supposed to be on Zoom to give your talks. So please register to get the Zoom link. If you don't remember how to do that or where that is, the registration link is in Mark's email. So if you can't find that, Mark sent an email on November 3rd. The title was BARS 2020 Speaker Information. This is just for you to search this email. And you'll find the register link. You can register. You'll get a link out of that. And you can just join Zoom. Okay. All right. And then one last thing is Slack. So as I mentioned, every group and every company has a Slack channel. So when you go over on our Slack channel, the channels don't necessarily show up because there are a lot of them. So just go under channel browser and you can see all these different labs. And if you go under each one of them, you'll find their material. You can talk to people, you can DM people. So that's a way of coordinating. We also have recruiters from companies. So feel free to go to the company's Slack channels and talk to people over there. Actually, with that, I really want to thank our sponsors for continuing their support of BARS over the years. And these are our sponsors. And with that, I think I just want to thank my co-organizers. So I've been chairing the session and this BARS this year, Dorsa Sadigh. My co-organizer this year is Mark Mueller from Berkeley. And I also want to thank Erdem, who basically did a lot of the work. So if you run into him, you should thank him. Okay, so with that, I think we are ready to get started. Again, reminder, this is the schedule. If anything looks weird to you, you can contact any of us. Actually, these are our email information too. You can message us over Slack. You can message over YouTube if you have any questions. We monitor all of that. Okay, so the first set of faculty talks is going to start at 8. We are 2 minutes early. Maybe we could start it even. And Mark will be moderating. So I'm gonna stop sharing screen and see if Pieter is here. Pieter, are you here?
Hi, Dorsa. How are you doing?
Good.
Thanks for organizing.
Thanks for joining us.
So, shall I try to share screen? Or Mark, did you want to do anything?
Sure. No, I think, Pieter, you can go ahead and share your screen. I think let's wait until the official start time. From my side, maybe as well, just welcome to everyone. Very excited to do this, even if we have to do it remotely. I think the biggest advantage of doing it remotely is there will hopefully be no complaints about the coffee and cookies this year. But I guess let's see. But yeah, Pieter, why don't you go ahead and see if you can share your screen?
Can you see that?
Perfect.
Yes, yeah.
Great. Yeah, also no commuting, right?
No one stuck in traffic, hopefully. All right, so just some information for the speakers. We have given you guys about 6.5 minutes each. We have a bit of buffer in there, but I mean, I expect there will be some friction in terms of flipping the Zoom. So I'm going to give you a warning about 5 minutes in, and that's when you should be wrapping up. So please try to stick to the schedule. And then there will be time for questions. And I encourage everyone listening online as well, please put your questions in the YouTube, and we will then moderate that. With that, Pieter, it's a big pleasure to have you here. Just again, Pieter is one of the original BARS organizers. It's always a pleasure to see him here. Pieter, why don't you go ahead?
Thank you, Mark. And yeah, Mark and Dorsa, thank you so much for organizing and having me. What I'd like to talk about today is something we've been working on quite a lot over the past year, which is in deep reinforcement learning, can learning from pixels be as efficient as learning from state? And to kind of situate this where things were about a year ago, this would be a typical learning graph comparing learning from pixels to learning from state. And so horizontal axis here measures the amount of training data collected. The vertical axis is performance, higher is better. And so what you see is that there's about a factor 100 difference in terms of how much data is needed when you learn from pixels than when you learn directly from the underlying state. And to some extent, maybe that's not a surprise because underlying state is the essence, what you need to do control. But at the same time, the information is present in the pixels. So in principle, you have it, you just didn't extract it correctly. And so the question is, can we bridge this gap? And so for many of you, this might remind you of the Jan LeCun LeCake, which essentially says, hey, learning for control, reinforcement learning, it's all great, but actually it's just a cherry on the cake. Most of the learning has to happen separately as representation learning. And if you do that well enough, you don't need that much data for learning to control. And so that's a hypothesis we started to investigate. To give a bit of context, I'll talk about two papers, Curl and Rad, and then do a discussion of how they kind of complement each other. So starting with Curl, what's the key idea there? We said, okay, we want to learn from pixels. So as we collect data, we put it in the replay buffer. Then we take data from the replay buffer. It's going to be images. We feed it into an encoder, and it goes to an actor and a critic. But then in addition to that, what we'll do is we will actually generate two different augmentations of the same observation and have an auxiliary loss that says if two augmentations come from the same observation, the embedding should be close. And if it comes from something else in the replay buffer, then it should be far apart. So that's the contrastive learning loss, recently kind of maybe like pioneered / reinvented by Aaron Vandennoord at DeepMind, but then the big breakthroughs were from Jeff Hinton's SimClear in Vision and Keming Ho's MoCo. So very similar to that. What we do is really think of it as translation or cropping is the data augmentation we use. So it means that our system should understand what it's looking at, independent of whether some things are partially cropped out. Then there's a couple of things you have to choose. One thing is whether you use an inner product weighting matrix or not. In the info NCE loss shown at the bottom left, we found that actually it matters a lot to have that weighting matrix, get to learn that compared to just the cosine loss. Then the other thing that kind of came out of the MoCo paper is to use an exponentially moving average for one of the encodings rather than just the current encoding. And again, we found empirically that that actually matters quite a bit here too. So assuming we do all that, let's take a look at the results. And this is in many ways the main result I want to present here, which is showing in gray, soft actor critic, one of these standard state-of-the-art reinforcement learning algorithms, in gray when run with state as input, and in red when run with pixels as input, and of course also the auxiliary loss for representation learning that I just described. And what you see here is that the red curve almost always closely matches the gray curve, meaning that this at the time was the first time that, and this is for DeepMind Control Suite, that we have very close matches between learning directly from pixels versus learning with access to the underlying state. If you look at after 500,000 steps and 100,000 steps comparing curl, which is our approach, with other methods that are somewhat tuned to take advantage of pixel inputs, we see that it pretty much consistently outperforms those past methods. And on the Atari games, it often matches or outperforms model-based methods, which are supposed to be more sample efficient. The most effective model-based method for the 100K frames is simple. And then the kind of most effective method for longer learning tends to be Rainbow, and curl here is on top of Rainbow. So auxiliary loss added to the existing Rainbow algorithm. Okay, some ablations. Sometimes it doesn't work as well. We then investigated those environments and saw that if you keep learning forever, it still doesn't get the same performance as learning from state. So maybe something fundamentally is missing in those environments when you learn from pixels. We then did supervised learning from pixels onto state and found that supervised learning could not recover the state, suggesting that for those environments, the pixels don't have the right information. This is not too surprising. This could be true in robotics because the pixel values don't expose, for example, forces, contact forces, which for some environments might be quite beneficial to do control. Can we learn without reward? It's a question, okay, do you need reward from the beginning? Can you just train a representation and then after that learn the actor and the critic without backpropagating into the representation learning part? And mostly you can, not exactly as well, but mostly you can. Then one other study we did, and it looks like we have about a minute left, is to see if how much we can get from just data augmentation. Get rid of the auxiliary loss, just do massive data augmentation and reinforcement learning, which we call RAD. So instead of feeding it in, you feed in data augmented versions.
Pieter, you're going to have to hurry a little bit because there are minutes for questions too.
Okay, got it. So if you look at the learning curves here, that's maybe the main takeaway. I'll end on this slide. When you use data augmentation, RAD, it actually often does as well as having a representation learning loss. So it seems like a lot of the strength of representation learning comes from the data augmentations. But of course, the downside of just doing data augmentation is that you cannot learn without reward. You need to have always access to the reward to learn the representation. Whereas if you do curl, you can learn a representation even before anybody provides any reward into the system. And I'll end here. Thank you.
Excellent. Thanks a lot, Pieter. Reminder, if there are any questions, please type them into the chat window. I don't see any questions yet. I have a question for you here, Pieter. Often when, as someone that's maybe a user for these kinds of tools, you're overwhelmed by the number of options. How do you figure out which is the right hammer to hit your particular nail with?
Yeah, love that question. Thank you, Mark. Many opinions, but I'll give one opinion. I would say if you have a very fast simulator, you probably want to use something like PPO, which is on policy and is constantly using new data, because very fast simulator data is effectively free. If you don't have as fast a simulator or a more expensive simulator of some kind, something off policy will often be more favorable to use. And then soft tactic critic tends to be one of the popular ones, as well as TD3. And if you want to go even more off policy, DQN type methods tend to be even more sample efficient, but sometimes a bit harder to get to work stably.
Perfect. Thanks a lot, Pieter. I think maybe I'll ask that, Koushil, if you can try sharing your screen. If there's any other question from maybe the other faculty on the line. If not, thanks a lot, Pieter. It's very hard to do this without applause. I think, Dorsa, next time, if we still do this remotely, we have to have like an applause track that we can play. Thank you very much, Pieter.
There's a question.
Next, we have Koushil Sreenath from UC Berkeley. Koushil, I'll let you take it away.
1 second, Mark. Just wanted to remind our respondents. So we have some student respondents. Feel free to ask your questions on YouTube. So you go monitor that. Again, like we have a number of students who are respondents for asking questions.
There's a question on YouTube chat.
Students at 8 a.m. would be very impressive.
Yeah, I think that's the challenge we're having. The students will need the coffee to kick in. Koushil, why don't you go ahead?
Okay, thanks, Mark. Thanks, Mark, and also for organizing this. It's great to be here. So I'm excited to share a little bit about legged robots beyond legged locomotion and learning for control. So I'm going to talk about a glimpse into a few projects. So let's look at emotive dynamic characters. So this is a project with Zhongyu and Christine. So if you look at virtual characters on the screen, like movies from Pixar, they're very emotive. But if you look at robots in the real life, the only time when they look lively is when they fall or when you speed up the video. Now, how do you bridge these two things? So we've been looking at developing tools. So we can develop animation tools to create all kinds of emotive motions, but you can't put these on real robots directly. So there has to be a framework to do this. So you can build up tools, you can give this to an animator, but then you have to do an optimization to make sure that the animation is dynamically feasible before you can actually deploy it on a real robot with control. So here's a glimpse into some of the behavioral design that you could do. So you could design motions, you could design expressions, and this was how it would look on a robot when you would render it with a dynamically feasible motion and a controller in action. So I'm just showing you something where the robot is standing, but you can also make this walk around. So I'll let Zhongyu talk more about this in one of the sessions later on. Okay, so I've also been recently interested in using manipulation for locomotion. So this is a project that I proposed to a couple of students. So how do you take this quadruped and manipulate a ball? If you look at our canine friends, I mean, they're really good at doing this. This is an example of highly dynamic motion. They're trying to unify manipulation, locomotion. So we will try to do this. That's where we are headed. We are nowhere close to doing this. So let's look at how we can do this. So you could develop equations of motion for the robot, for the ball. You could combine it. You could develop a controller for this together. At least in simulation, this works pretty well. You could do all kinds of locomotion on the ball to manipulate it, trotting, bounding, pronking. You can follow desired trajectories that are straight lines, sinusoidal, curved around. You can also turn around on the ball, which is pretty cool. So we are headed towards experiments. Our first preliminary experiments are actually inverting the problem, where the ball is being manipulated with the robot being fixed. So we hope to invert the ball problem again and try to test this out. Okay, so let's look a little bit into using reinforcement learning for safety critical control. So this is work by Fernando and Jason, and joint work with Clay Tomlin. So we have a robotic model of a system, but the problem is our model is not precise. This is true for any dynamical system. So how do you develop a controller that can guarantee stability, that can guarantee safety, but you do not know the model? So if you knew the model, you could do nice things. So you could design a control output, and the goal of the controller is to drive this output to 0. You could use a traditional controller like an input-output linearizing controller that cancels away all the nonlinearities and gives you a linear system. So this is how I/O linearizing controller would look like. But the problem is you do not know the model precisely. And if you do I/O linearization with the imprecise model, your I/O linearized system now has model uncertainties, which are nonlinear. So what we've been looking at is how to use this with Lyapunov functions. So the time derivative of the Lyapunov function depends on the model, f and g. If you do not know the model, then it has this uncertainties delta 1 and delta 2. And it turns out you can create a network to learn these uncertainties delta 1 and delta 2 by using these parameters alpha and beta. So alpha and beta parameterized by network weights theta. So you can create this quadratic program that's also parameterized by network weights. So you could learn this through data. So this is what you do if you learn it with an uncertain model. So the blue one is a reinforcement learning based control Lyapunov function quadratic program. And in comparison, we're comparing it with the L1 adaptive control. So if you look at the bottom plot, the friction constraints are violated when they go beyond 1, and a robot would fail. You can also test this with something that you haven't trained on, and it still works. And we've extended this to constraints, barrier functions, and so on. So you could take your model that's a nominal model, combine it with the network, create a quadratic program, and you can get a safety critical control with walking and stepping stones. Okay, so the last thing, I want to provide some preliminary results. This is work with Zhongyu, Jason, Shushin, and Glenn, and also joint work with Sergey and Pieter. So we wanted to develop reinforcement learning for CASI. I never believed that this would actually be possible, but it's always nice to be surprised by what students can achieve. So here's a network that learns the desired trajectories to apply on CASI to achieve various locomotion motions. So we learn in Mojoko, do dynamic randomization, and then test it on a high fidelity simulation before we go to experiments.
30 seconds, Koushil.
Perfect. And then we deploy it on a robot. So it turns out the very first experiment on CASI actually works if you follow this. And you could do all kinds of crazy motions, and it's also robust to perturbations. All right, so thanks for listening. Happy to take questions.
So thank you very much, Koushil. Questions from the audience. I think there might be a delay in the YouTube questions section. I know we got a question for Pieter halfway through Koushil's presentation.
I don't know.
Sure, go ahead, Anca.
So I'm really excited about the very first thing you talked about. And I'm wondering how we can work on automating those motions to begin with, so that you don't have an animator needing to draw them out, but you can get the robot to actually figure out how to move in those expressive ways like that. That's something that is still a problem near and dear to my heart, and maybe we should figure out how to collaborate together on that.
Yeah, so I've been meaning to reach out to you as well. So I think it'd be great to go from emotion to motion. So if you could learn something like that, then you could deploy it on a robot.
Yeah, that'd be really cool. Okay, I'll send you an email, Koushil.
Okay, Anca.
Excellent. Thank you very much, Koushil. Of course, one of the original goals of BARS was to get roboticists to work together. So I'm very happy to hear this happening in real time here. Up next, we have Dorsa Sadigh. Dorsa, I guess we'll know you at this point. Why don't you go ahead and see if you can share your screen again?
Sure thing. 1 second.
Okay. So there's a question to Koushil. Can you hear me now?
There we go. I
we
can
hear
hear
you.
you, Adam.
Okay. So yeah, should I ask the question? It's from Ash Robbins, and it's asking, is the higher fidelity math simulation necessary for sim to real?
So is the higher fidelity simulation for sim to real?
Is it necessary? Is it needed for this?
So it's unknown if it's needed. So at least in practice, we've seen that it helps. We don't know if it's required for sure.
Okay, thank you, Koushil. Okay, Dorsa, why don't you go ahead?
All right. Okay. Hi, everyone. So today, what I want to do is I want to talk about a broad set of things that you're doing in my lab over the past year and in general. So I'm going to do a list, basically, of some of these directions that we are looking at, not going deep in one project. And in general, I'm going to talk about 2 sets of categories of work. One is this idea of learning human preferences, where we treat this human as this agent who has all the information, and it's just trying to teach a robot how to do a thing based on different sources of data that it has and that is available. And then after that, I want to take a more symmetric approach, more dyadic type approach, where we have the human and robot coordinating with each other on a task. So let me tell you a little bit about what we have been working on in these 2 main areas. So on learning from humans, in general, this idea of learning reward functions or learning policies has been around. This idea of learning it from expert demonstrations has been around for more than 2 decades, right? Like imitation learning has been around for a long time. But some of the directions that we have been thinking about is to try to think about other sources of data that are available to humans, right? Like we could go beyond expert demonstrations, and there are many other sources that we could actually tap into in order to learn what humans really want or what their preferences are. So my group has been looking at a variety of different avenues here, and I'm going to briefly mention some of them. So we've been looking at this idea of learning from suboptimal demonstrations and observations. This is a popular area these days, this idea of learning from observations that are not necessarily expert or optimal in any ways. So what Junjie has been looking at is combining expert demonstrations from agents with different dynamics, and suboptimal demonstrations in one giant data set, and trying to estimate what the feasibility and optimality of each one of those demonstrations are. And then based on that, being able to do imitation learning from these different samples that have different optimalities and feasibilities. He will be talking about that in one of the spotlights a little bit more. If you're interested, you should talk to him over Slack. Moving forward, another type of source of data we are looking at is language instructions. So Sid has been working on that. And the idea that he's been looking at is thinking about interactive teaching. So if the human comes in and says, wash the coffee mug to a robot that doesn't really know how to go about it or how to do it, the idea is we can have interaction data between the human and robot. And what we want to do is we want to learn from decompositions that are generated by humans. And based on those decompositions, we're going to be able to figure out which part of these interactions correspond to washing the coffee mug and which parts actually don't. And how do we combine that with historical data is the question we are looking at in an online learning fashion in order to interactively teach a robot how to wash the coffee mug, like in the next iteration. So again, Sid will be talking about that more in one of the spotlights if you're interested in that area of robo-NLP. Other types of data we are looking at is pairwise comparisons, rankings, and ordinal data. So Erdem is very interested in this idea of active preference-based learning in this domain. So when you have 2 different trajectories, for example, and query a person and ask a person, which one do you prefer, or can you rank these? How are we going to learn reward functions? And it turns out that linear rewards are not really able to capture everything here. Like for this version of mini golf, like where the robot is trying to play mini golf, it is not really able to capture like what the target is. So we've been looking at using Gaussian processes here and active preference-based learning over Gaussian processes in order to better figure out what the reward function looks like. Skipping the math, but just to show you how the linear rewards look like, they end up pushing the ball towards the corners. But when we use the GPU reward, we are able to actually capture each one of these, like what is the target preference here. And then finally, I want to emphasize that a robot is not an AI agent, right? It does have an embodiment. You can move it around. And because of that, I do think we should tap into physical corrections. And something that Mangshi has been looking at is how could we combine, how could we learn from a sequence of corrections that are provided on a robot, on a complex multi-agent system? So in this case, the two robots are trying to help the person, let's say, unpack groceries. And what the user is doing is providing a sequence of force corrections. And based on that, the idea is how can we understand the interdependencies and learn a reward function from that? So moving forward, that's all about learning human preferences, but we've been thinking about using these types of human preferences in interactive autonomy, in better planning and coordination. And for that, we've been looking at this idea of risk-averse human models, the fact that our human models are not always like accurate, specifically when we are thinking about near accident driving scenarios or settings when humans are acting suboptimally. What Mene has been looking at is basically maybe there are different ways of modeling these types of risks and biases. So if you think about what I've been talking about so far is we can learn a reward function, we can assume humans are optimal and take rational actions. You could even like assume humans are noisily rational. Maybe they're following some sort of probability. What Mene has been looking at is the fact that sometimes the most likely
time warning.
Okay, yeah, time warning. Okay, yeah. Sometimes the most likely action of the human is something that is suboptimal. So she's been thinking about using these types of risk-aware models for settings where humans use these suboptimalities for better coordination. One other idea we've been thinking about is using learned representations for better interaction. Dylan has been leading this for teleoperation, where we are using demonstrations, and based on those demonstrations, we are learning latent representations of actions. And based on that, we have an easier time doing assistive teleoperation, getting a robot move around with like just 2 degrees of freedom in a much more intuitive way. And this idea of representations has been, like we've been using it in other settings where we are thinking about interactions a little bit more carefully, like collaborative transport or playing with a robot. So Annie will be talking about our work around learning latent actions and coordinating and influencing with humans. And finally, one thing that I'm really excited about, and I don't have much time to talk about, is this idea of repeated interactions. So over repeated interactions, what type of behaviors emerge, and how could we realize that there are different partner-specific things and rule-specific things that we could differentiate between, and think about what are the types of conventions that get evolved based on coordinating with different partners and new partners. And that's something that Andy has been thinking about. So with that, I'd love to answer any questions if there are any in this group.
Thank you, Dorsa. A note here, I note that the screen was being cut off, but I think this has been fixed. Hopefully, if you're still seeing issues with your stream being cut off, please let us know, but I hope it's fixed. Thank you. Are there any questions on the YouTube? I see there's a lot of chat. I see Pieter is very busy there. That's excellent. Thank you, Pieter. Any other questions? Any questions from our panelists? Okay, if not, then I guess Dorsa, you'll have your lab chat up on the Slack as well. So I'm hoping that the Slack takes off too. And then up next we have Ken. Ken, it's a pleasure to have you here again. I hope your daughter has been writing more books. Last year we got to give some away, so I'm looking forward to anything like that. But then I'll give you the floor, and I'll give you a time warning about 5 minutes in as well. You're still muted, Ken.
That is a rookie error. Okay, sorry
there we go. Now I can hear you. I've lost your screen though.
Okay, I'll share the screen again, and here we go. Okay, good.
Perfect.
Can you see the screen? Okay,
that's good.
All right, thank you. All right, thanks, Mark. And what I want to talk about is 3 new results that I'm very excited about. And the first one was presented at Coral this week, and by 2 of our superstar undergrad, one an undergrad, one a master's student. And it's about untangling knots. And this is a really nice problem because it's very commonly encountered in reality. I mean, we all face this challenge at various times, and it's important because this can be tripping hazards for senior citizens. And so it's a very high dimensional problem. Also that the rope or cable is self-similar along its length. So visually, it's very hard to identify key points. And in addition, the manipulation part of it is that there's challenges in terms of actually grabbing a hold of very small points and holding on to them. So it's a bilateral problem. And there's a number of other aspects that are covered in the paper. So this actually is a little bit similar to what Pieter talked about curl, about having full state information, which is where we start, where we have a simulation, and then where you just have pixels. where you're just looking at the cable. And that's what we want to, that's what we're going toward, right? We want to be able to just have observation and reality and then be able to untie these knots. In particular, we're looking at knots that are dense, that don't have open space between them, because that makes it particularly challenging. And so this is examples here in sim of what those dense knots look like. There's a huge body of related work out there, in particular a paper by Louis and Ashutosh that was in 2013. That's particularly interesting, and we drew from. The problem statement is you have a semi-planar scenario, so we're not looking at knots stacked up on top of each other. And we're going to do a sequence of actions with the bilateral manipulator. And we actually use the Da Vinci in these experiments because it actually has very nice precision and very good grippers for this problem. And we developed two algorithms. One is we call Bruce, and the other is called Hulk. And you can understand the details of that in the paper. We're sort of drawn, inspired by the superhero. And they did a very nice thing of learning, first of all, how to tie knots in simulation. And then we did experiments in sim and showed that it was very successful, this algorithm, when you have underlying state. But then in real, we then hand labeled images. I should say Jennifer and Priya did. And then these are some of the results. So they're able to, with these essentially drawing on knot theory, to be able to perform these two primitives reliably and find these key points in on the cables. And so we're able to routinely untangle knots like this. They don't work all the time, so about 62% in real. And it's because there's a lot of sort of a manipulation effects. The rope gets stuck in the gripper. So there's a lot of other work to be done here. It's an ongoing project. We want to look at multi-cable untangling. So welcome collaboration on this. The second project also has to do with ropes, and this has to do with the idea of dynamic manipulation of a single cable or rope. And this is motivated by the problem of trying to vacuum a carpet where you end up getting the cable caught around some chair or something. You have to kind of whip it over the chair. So this is work with Harry and Jeff, Jeff is going to be on the job market this year. So keep him in mind. We were inspired. The title of this is Robots of the Lost Ark, ARC. And so we did these experiments. This is now under submission to ICRA. And the nice thing about having one end mounted on the plug is that you actually get a reset capability. So there's a way of learning the key here is learning an apex point that is able to achieve. And these are the three tasks that we're doing. One is called vaulting, which is over an obstacle. The second one is knocking, which is being able to essentially knock off an object on an obstacle. And the third is weaving. And the input to this is an image. So the camera looks at the scene and then basically tries to infer this apex point. So lots more work to be done there. We're also having two presentations in the poster sessions here.
Intermittent visual.
All right, that's a result, a beautiful result on with our surgical robot that Minho, who's postdoc, and Sam.
Time warning here as well.
Intermittent visual.
Okay, and the last one is we were really fortunate to have a paper that came out on Wednesday. That's on the cover of Science Robotics. And this is about very high-speed motion planning for grasping. And Jeff will be talking about that in one of the posters. So I also want to just do a quick plug. We have a startup that's doing robot manipulation, and it's called Ambidextrous. Anyone's interested, just contact us. This is a thanks to all our sponsors. And if you wanted more information on the papers, they're available at my website under new papers. Okay, thanks.
Excellent. Thank you, Ken. I love this. This is so interesting. And it's such a relatable task on the one hand and so incredibly complicated. I can't even imagine how a robot would even begin to do this. So I think it's a fantastic research challenge to go to. Are there any questions on this, the YouTube? I wonder if the YouTube is again delayed. I see that the questions are not coming up. I just want to make sure that I'm not missing any questions from the audience because I don't want to take all of our questions. I guess on my side, Ken, a question I would have is, I guess a lot of the application here might be towards cables, which have potentially different stiffness from, say, a rope. Is that something that matters a lot? Is that, is this something that's easily learned, or are there challenges there?
No, you're absolutely right. I mean, if you have stiff cables, then there's lower turning radius, right? So or higher turning radius. So basically that's a big advantage. We did some experiments with string, and as you get down into smaller and smaller strings and threads, of course, it gets more and more difficult to be able to reach in there. So absolutely, that's something we want to work on. And there's also an opportunity here in active sensing to be able to actively move around the knot and search for places, opportunities to grasp it. So both of these are really at the early stage. And again, I want to emphasize that we're really excited about this and very willing to work with others on this at DARS. Please get in touch with us if you're interested.
There's some questions here. Let's go through some of these questions quick, because I think we have a little bit of slack time here. I guess one question is what is the minimal information about the robot needs to learn about the cable to do this? I guess stiffness might be one thing. What else would sort of be the minimal information?
Well, currently we don't actually. It doesn't have any model, right? So we're trying to generalize from examples. So in this case, we have trained it on a number of examples in real of the key points, the pin and pull points, and then we showed it's the same that we're using for now, the same cable, but now in new configurations. So one big question is, how is it generalized to a different rope configuration and to different kinds of knots? There are other overhand knots and other kinds of things that we want to tackle. And then we also want to look at knots on top of knots. So compound knots that are non-planar.
Excellent. Thank you, Ken. Once you figure this out, I have some old shoes that I'd love to bring by. All right. I think then, Allison, we'll move to you next. If you can share your screen.
Sure. Can I just make sure you can hear me first?
I can hear you fine. Excellent. So up next, Allison Okamura from Stanford. Allison, I'll give you also a time warning, about 30 seconds left.
Great, thanks. So I am really happy to come to you today to talk about robotics for assistance and understanding of human sensory motor deficits, particularly for individuals with stroke. And I should mention there are some related topics in terms of haptic perception, as well as prosthesis assistance that will be coming from some of my students later. But here we'll talk about stroke. So specifically, if we think about the human motor control system and the challenges that it has, when you have a stroke, you have problems with this control block, knowing, having your brain know what it needs to do, even if the dynamics of the body are perfectly intact. And another problem that's often overlooked is the estimation problem of knowing where your body is in space. So one of my recently graduated students, Sean Sketch, particularly was interested in the role of proprioception, that is the sense of where your body is in space, which can actually be quite degraded in patients who have had a stroke. And so using an exoskeleton robot, he ran a number of human subject studies in both healthy people as well as patients with stroke, looked at both passive movements as well as a couple of the active movements in both joint space and task space. As we know, robots can be controlled in both spaces. And with people, we also wanted to explore how those spaces affected their motor control. And he had a lot of interesting results, but let me just highlight one, which is that if you looked at the proprioceptive ability, the acuity, which is shown on the horizontal axis of stroke survivors, and compare that to perceived motor deficits, we found a strong correlation, meaning that when we think about people with stroke and how do we help their motor ability, we cannot just focus on improving their motor skills, but we also need to improve their perceptual skills. So another patient population, this one actually is not stroke, but for patients with spinal cord injury, and perhaps maybe one day this could be applied to stroke. Researchers at Stanford and elsewhere have been applying electrode arrays to the brain in order to record brain activity, do a decoding, and then send command signals that could control a cursor on a screen or even a robot arm. And here we were interested in looking at providing haptic feedback through a desktop robot-like haptic device in order to provide better proprioceptive feedback. Since the patient can't actually move their arm, we're providing haptic feedback to give the idea of movement beyond the visual feedback that they get from seeing a cursor on the screen. And in this particular patient with spinal cord injury, there was only tactile perception from the neck up. So we characterized that and decided that that's where we had to provide haptic stimulus, is on the back of the neck. And we found that we could correlate the stimulation on the back of the neck to responses in motor cortex, so signals that we could measure on the electrode array. And the feedback could be useful during this invasive BCI control, brain-computer interface control, and it didn't interfere with BCI performance. So this next slide shows a video of this patient using the brain-computer interface to control the cursor on the screen and receiving haptic feedback at the back of the neck as a form of proprioceptive feedback to augment the visual feedback he already has. You can see recordings on the right of what occurred in the electrode array, as well as measurements of his shear perception accuracy compared to our ability to neurally decode the information from the electrode array. And the correlation between those two plots shows that the haptic perception is well matched to the task. So that is, again, not in stroke, but going back to stroke and other movement deficits, in addition to providing haptic feedback, we can actually provide, of course, real physical assistance. And so my recently graduated student, Cole Simpson, who I believe, if he hasn't been snapped up already, is still on the job market. Cole was interested in specifically targeting an issue that can occur in stroke where patients have abnormal motor synergies. In particular, if they, for example, move their elbow up against gravity and have to support the weight of the arm, they are then not able to move in the plane. And so specifically, he looked at designing simple and relatively passive devices, both soft and hard, which have their advantages and disadvantages, which showed that by providing support in one degree of freedom, it enables more movement in other degrees of freedom. And we hope that this type of technology can be distributed fairly easily to stroke patients because it is relatively low cost and simple to don and doff. So finally, if we want to provide true rehabilitation rather than assistance, we have to think about how the brain can get rewired from stroke. Thank you, Mark. And so one way to do this is through haptic feedback. And my postdoc, Caitlin Syme, has been looking at wearable tactile devices from a kind of wearable computing perspective, which are simple, low cost, can be worn during activities of daily living. And what she's found is that vibrating on the skin and perhaps also targeting muscles and tendon, she is able to use the haptic feedback to have patients regain both haptic perception capabilities as well as movement capabilities. And this would be great compared to your typical exoskeleton robots that are used in these kinds of procedures because, again, it's so inexpensive and it's something that can be used in the home. We actually have some very open scientific questions because we don't know exactly how or why this works. And we have some funding from the National Institutes of Health to try to discover the underlying mechanisms and examine the hypotheses mentioned here. So in conclusion, I want to thank the students and postdocs whose work was especially featured here, our collaborators, and our funding agencies. Thank you.
Thank you very much, Allison. I must admit I was kind of lost in your presentation. I didn't see the time, so I think we went slightly over time there. Are there any questions? Maybe a quick question from the YouTube. There's a question here. Ali asks whether you consider grasp taxonomy and grasp synthesis in this work.
Oh, that's a great question. I definitely think you could. At the moment, we're so worried about very simple degrees of freedom of movement that we haven't really considered grasping, but especially for stroke patients and of course, even patients with spinal cord injury, the ability to have all those degrees of freedom in order to truly manipulate and perform dexterous manipulation is key. So I think as we expand these ideas to higher degrees of freedom, we could absolutely connect this to ideas in grasp synthesis in order to provide assistance and rehab.
Excellent. Thank you very much, Allison. Up next, we have Chelsea. Chelsea, I can see your screen fine. I think you can go ahead.
Great. Hi, everyone. I'm an assistant professor at Stanford, and I'll be talking about data scalability in robot learning. Our current paradigm in robot learning is to train robots to do tasks individually, completely from scratch. And while this has led to impressive results, like a robot that can use a spatula, this approach is also problematic. The problem is that the robot didn't learn how to generally use spatulas, but the robot learned how to use that spatula to lift that object into that bowl. Its entire world is this one scene. This is essentially analogous to training a baby from day one to use a spatula without a regard for anything else in the world. And as a result, these robots fail to generalize to the breadth of the real world. Thus, today I'd like to talk about how we might allow robots to learn from a breadth of diverse experiences, not just a single task in a single environment. So this involves two parts. First, how do we scalably collect data? And second, how do we leverage that data? So in terms of scalably collecting data, one approach is to simply program the robot to take random actions. This actually leads to surprisingly interesting interactions in data, and we can also collect a lot of data this way, including running robots overnight. However, the utility of this data is still quite limited. Another approach for getting more interesting data would be to provide demonstrations to a robot. This leads to very useful and interesting data, but we can't collect a lot of data this way because it requires a human in the loop of the data collection process. So how might we collect data in a scalable way without a human in the loop that also leads to interesting data? To do this, our approach is quite simple. First, we show the robot examples of a few interesting states, such as interacting with a particular drawer that the robot will need to use in the future. And then we train the robot to simultaneously classify between these interesting states versus data that the robot has explored so far, and train the robot to explore images that are found and classified by this classifier as interesting. And if we do this, if we give the robot just less than 3 minutes of human guidance and then run autonomous exploration with regard to this learned classifier, we see that the robot can figure out how to interact with the drawer and collect lots of interesting data with regard to this target object. And in comparison to state-of-the-art approaches that try to explore in a task-agnostic way, we see substantially more interaction with the drawer handle and the drawer in comparison to those approaches. So that's one way that we can go about collecting data. Another really interesting data source is videos of humans, such as the Epic Kitchens data set shown here. This is a really large and potentially untapped data set for robot interaction. There's loads and loads of interesting data here. But of course, it's not clear how robots might leverage this data. So how might we go about actually trying to tap into this data source of videos of humans? In particular, we recently studied how we might leverage videos of humans for a particular task in combination with online robot interaction in the robots environment. And the key idea that we wanted to study is whether we could simply add the videos of humans to the replay buffer of a reinforcement learning agent and train the robot using both the human's experience as well as its own experience. Of course, we can't just add the videos of humans to the replay buffer because there is domain shift and the videos don't have actions or rewards. But we can use simple approaches to address each of these three challenges, using domain confusion and some approximately paired images, using a learned inverse model to predict or approximately predict the actions of the humans, and also a simple scheme to label rewards by labeling the last state as having high rewards. And what we find is we considered two different manipulation tasks, opening a drawer and pushing a red puck, both with sparse rewards and raw image observations. And in both environments, we see that leveraging the experience of humans leads to a 2x gain in the robot sample efficiency compared to standard RL, where the approach of leveraging the human experience is shown in orange and standard RL is shown in green. So to take kind of the key takeaways of what I wanted to convey in this talk is, first, robots need to learn from broad and diverse experiences if we hope to allow them to generalize to the real world. And I talked about one approach about how robots might autonomously collect useful data, which may allow the robots to collect broader and more diverse experiences, and how robots can effectively leverage human experience to learn faster, which may allow us to tap into an extremely broad and diverse data set. And I'd like to thank the students, Annie, Suraj, Alex, Carl, and Ole, who did a lot of this work. Thank you.
Excellent. Thank you very much, Chelsea. Questions from the YouTube channel or from the panelists? Sorry, time call alarm is going off. So Chelsea, you were very on time, so thank you very much for that. A question I have here is this feels a little bit like, breadth versus depth in search, right? I mean, do I overtrain for one task first and then generalize later, or do I sort of dart? Is that a fair analogy, or is there, something, is that not an apt?
Yes, I think that's a great analogy. And I think that the issue with the depth first search that we've been doing so far is we typically just do the first step of that depth first search, and we don't actually extend that depth first search to actually continue to allow the robot to learn more tasks and learn how to solve more things in the environment. And I'm also I'm in favor of either depth first or breadth first, as long as we ultimately have a mechanism and a path to get to a robot that can do things in many different environments in the real world.
Excellent. Well, thank you very much. Thank you, Chelsea. Chelsea will be hopefully on the Slack, or at least some of our students will be on the Slack as well. Up next, we have Monroe Kennedy from Stanford as well. Monroe, I see you're online.
Yes, here.
Perfect. I can see you and I can hear you.
Fantastic. So thank you. My name is Monroe Kennedy. I'm an assistant professor in mechanical engineering at Stanford University. And I'll be talking about research being done in the ARM lab, where we focus on collaborative robotics. So our lab focuses on three main areas: robotic assistance, intelligent wearables, and connected devices. And our goal is to develop systems that are intelligent and assistive and can improve human life. So when we think about robots actually working together with humans performing complex tasks, it's extremely important that the robot be able to model itself, the task, as well as the human in the loop to be effective. We've been running for about a year, and these are all of my fantastic students who are working across all of these areas. So the question I want to ask today is, why is human-robot collaboration valuable? You can think about minimizing risks to first responders, providing increased autonomy through assistance, and even providing superior strength and stamina, which may minimize a risk to human collaborators. So we see that it's very useful to have these collaborative robots, but what does it take to actually make them realizable? I would argue that the two main things are that they be capable and collaborative. So capable, the ability to reliably perform tasks, and collaborative, to be able to work with and adapt to their human teammates. And so today I'm going to just look at two projects within our lab that are really addressing these two areas broadly. The first one is our project in dexterous manipulation. So hopefully a lot of you have seen this video before. It's an amazing video. The hand is manipulating a Rubik's Cube with just a single hand, and there are cameras looking in that allow it to train and do this. However, it took a very long time to actually train to do this single task, and no haptic information is actually being used. No contact information is being used. So if you had better finger sensors that could give information about the normal and shear friction forces, the question is, if you had those models, would this actually be easier to train, and would it be generalizable to a broader set of manipulation tasks once you learned some useful features for one of those tasks? You could think of many domains where these types of manipulation could be very useful. It could be in assisted living, could even be in manufacturing processes. Both would be huge strides forward. So the question really becomes, what makes this difficult, right? As humans, we're able to manipulate a range of objects, and we're able to do so by leveraging knowledge of friction when we're contacting an environment, as well as we have very deformable 3D fingers, which make it possible for us to manipulate small objects very well. There's been a lot of work over the years with this and a lot of amazing progress, but we're still getting closer to having these systems that are very capable and approaching human dimensions and abilities. So we break this problem down into three main areas: design, model, and motion planning. Given our time today, we're just going to focus on research that we've done in the space of design, but we've also made strides in modeling as well. My student Wang Kyung Do has developed a sensor. It's a fisheye lens camera that observes the interior of the deformed surface and allows us to actually measure the deflection of the surface, the normal and the shear forces, similar to other sensors on the market in this space. So this is a video of our sensor working. We slowed down the rate at which the LEDs rotate, but this will allow our camera to have multiple perspectives when the sensor is actually being deflected. Within this first design phase, we're really wanting to add the component of giving the sensor an actual calibrated force measurement. And with this, we think we can augment those abilities to actually model our system really well for our contact. In the last minute that I have, I want to talk about the collaboration side. So in this project, we're looking at how we can help people with full shoulder disarticulation. And we think we can make the robot arm really intelligent, where it can observe the environment. And if you can sense information from the human, what they care about, what they see, and whatever you can get from them, EMG measurements or mixed reality, can this help the robot arm ascertain what the human wants to do? So if you have a system like this, the question is, what does the robot replace and do in order to be effective as a teammate? So if you think about the human, all right, we have cognition, we're able to move our system, and we're able to sense the environment. Robots are becoming very capable, as you see in all of the talks today, and we can do all of these things. So what does it take to actually augment a human system in this way? So if you have just a prosthetic, you're replacing the physical aspect. You can give it the ability to sense its environment. And with all of this, now we can begin to plan as well. And so our goal in this work is really to understand the task, understand the human, and make the robot an effective collaborator. Thank you.
Thank you very much, Monroe. That's really cool. And you are very timely, and I appreciate that. Any questions? I think I probably am going too quickly. Questions on the chat? Not yet, I think. Just want to make sure I give folks who want to ask questions enough time. Any questions from my other panelists here? Otherwise, I'll go ahead and ask a question. Ken, did you have a question? No, okay, sorry. I thought you raised your hand. Monroe, this is very interesting stuff. I guess, you know, when you're thinking of intelligent arms, etc., how do you mean? Oh, sorry, Ken, go ahead.
Oh, sorry. Well, Monroe, I really like this new the sensor and the idea of the rotating LED. So I was wondering if you could say a little more about what you gained from that. In other words, the multiple perspectives from the light.
Right. So, you know, if you look at a lot of similar sensors, right, you have like the, you know, the inversion surface, you're getting the shadow displacements, which tell you if you have like a displacement or a valley, like a hill or a valley. But then, you know, in order to get a really good view of this, a lot of the existing systems that are there have static lights around the edge, right? And so the more the dimensions of, as the dimensions of your problem grow, and specifically if it's curved, like if you look at traditional like gel sight, it's really flat. As you make it more curved and you want to see that curved environment, it's really hard to get those multiple perspectives when you think about where you can actually place the LEDs. So by allowing them to rotate really quickly at a super high frequency relative to your contact rate, we believe that this is actually going to help us get those multiple perspectives, which are beneficial when you're actually looking at an extremely curved surface. And so that working with the fisheye lens, I think makes this a really viable approach.
Very interesting. Okay, great. Thank you. Oh, Mark, you're muted.
How the tables turn. What sort of collaborative tasks, Monroe, do you imagine doing with this sort of framework?
So referring to the second project, you know, the prosthetic arm, right now, you know, this is really like an example of an intelligent wearable. So the robot stands between the person and the environment. So if you wanted to do an activity of daily living, let's say you wanted to pick up your fork on a plate or pick up a cup, as I was showing like on the last slide, right? How can you actually understand what the human wants to do? And when there's a cluttered environment, actually take the right action based on the limited information you can obtain from the human. So in the best case scenario, we could do an activity of daily living similar to the way a human, an able-bodied person would be able to perform that task.
Excellent. Thank you very much, Monroe. Well, so I want to thank all of the speakers in this first session. I think that was really interesting. Thank you very much. I think, Dorsa, shall I give it back to you?
Yeah, so now we're switching to Spotlight Talks. Actually, Erdem is moderating this session. Erdem, are you there?
Yes, so Spotlight Talks will start at 9 a.m. So I think we can just...
Start,
I think we can start early, Erdem. I think that's fine.
Longer coffee.
Maybe just by way of introduction, the spotlight talks, these are all students of the various labs that are going to give smaller introductions to their work.
My name is Kara Welker, and I'm going to present work done in the Charm and Biomechatronics labs at Stanford entitled Teleoperation of an Ankle-Foot Prosthesis with a Wrist Exoskeleton. Active ankle-foot prostheses are typically controlled autonomously during human walking. With the goal of improving performance and better understanding human sensory motor control, we use a wrist exoskeleton to add teleoperation and sensory feedback, non-invasively restoring missing control and proprioceptive input. We implemented two types of control: position control with haptic feedback of ankle torque at the wrist, and torque control that allows the user to modify a baseline torque profile by moving their wrist against a virtual spring. We conducted a pilot test in which one participant with a transtibial amputation tracked desired wrist trajectories during walking, shown in blue, while we measured wrist response, shown in black, as well as ankle response. The participant was able to follow wrist trajectories with an average RMS error of 1.5 degrees after training, and the ankle also tracked desired torque and position below human perceptual error. For more information, please visit our Slack channels or check out our paper on bioRxiv. Thank you.
Hi, I'm Kim Lee. In this presentation, I'm going to talk about weighted Bellman backups for improved signal-to-noise in Q updates. As shown in this equation, Q-learning can be very unstable due to the error propagation from the next Q value. To solve this problem, we propose to reweight the Bellman backups based on some confidence score from the ensemble. The main idea is to downweight the objective function when the target value is very uncertain. And we found that this simple idea can stabilize the Q-learning by improving the signal-to-noise in Q updates. Additionally, we propose Sunrise, a unified framework that combines these weighted Bellman backups with UCB exploration and bootstrap. We found that Sunrise can significantly improve the performance of the overpolicy reinforcement learning method by handling many issues in overpolicy reinforcement learning.
Hey folks, my name is Sitkaram Chetty, and I'm a second-year PhD student at Stanford working with Dorsa, Sadigh, and Leon. I'm broadly interested in the intersection of language and robotics. So far, my work is focused on instruction following. Let's say I want a robot to wash the dishes, an instruction it's never seen before. One way the robot can respond is to say, I don't know what that means, could you teach me? To this end, we've recently put out work on learning from decomposition. The idea here is simple. Given a new instruction that a robot cannot understand, like wash the coffee mug, the robot asks the human to decompose their instruction into simpler steps that it can, using this decomposition to learn and generalize from. More recently, we've been looking at ways to learn from time-aligned language and demonstrations to build robots that can respond to language in real time. Complementing our prior work, this real-time element lets us correct robots on the fly as they perform new tasks. Looking forward, I'm interested in moving beyond instruction following. How do we use language to collaborate with robots? I'm very excited about this line of work and can't wait for what's next. Thanks so much, and I'm looking forward to the rest of ours.
Hello, I'm Zhongyu from Berkeley. I'm going to present our work on animated Cassie, which according to the best of our knowledge, is one of the first dynamic relatable robotic character. Creating robots with emotional personalities will transform the usability of robots in the real world. Robots need to be relatable. The whole idea of this work is to bridge the animation and the real-life robot, especially for person-sized humanoid robots, and to enable the robots to behave emotively with personalities. In this paper, we not only firstly create emotive character for a bipedal robot Cassie in 3D creation suite Blender, but rig the character in Blender with kinematics constraints. We also provide a direct collocation-based optimization schematic using full auto model to translate arbitrarily long animations to be dynamically feasible for bipedal robots. We are the first to achieve variable working height control on casting to perform designed LGR motions. And we build up an end-to-end framework to bring animations to real life.
We present batch exploration with examples for scalable robotic reinforcement learning. We study the problem of how best to collect large and diverse datasets for robotic manipulation. Our key insight is that we can leverage some weak human supervision before data collection to guide exploration, which comes in the form of a modest number of example relevant states. This enables the agent to learn to explore meaningful interactions guided by the human data while not needing human supervision in the loop, allowing data collection to be run unsupervised and at scale. Compared to novelty-seeking exploration methods, our method B interacts with target objects more than twice as often, produces data which yields improved downstream task performance, and is effective on a real robot. In our real robot setting, the robot needs to explore a small drawer on a desk. Given less than 3 minutes of human supervision, the agent is able to effectively explore the desk for over a day unsupervised, interacting with it more than an order of magnitude more than a novelty-seeking approach and improving downstream task performance. Please see our poster for more info.
Deep learning optimizes speed and precision of pick-and-place warehouse robots. This work appears in the latest Science Robotics issue. We looked at speeding up pick-and-place motions and their computation to alleviate a bottleneck. In prior work, we created an optimizing motion planer that incorporates a degree of freedom around grass contact points to generate faster trajectories. This planer refines a trajectory to minimize motion time and avoid obstacles, and results in high speed but also high jerk motions. We can see the difference between computed and executed trajectories. The high jerk causes overshoot and can lead to excessive wear. We constrain jerk, but this increased compute time. We speed up computation with the two-stage deep neural network. The first stage computes trajectories of varying length. The second stage selects the optimal trajectory length. These trajectories are not dynamically feasible, but they can warm start an optimization, which with a few iterations produces smooth and feasible trajectories and speeds up computation time by 300x, making it feasible for fast and long-term pick-and-place operation.
I'd like to present a new tactile sensor for dexterous manipulation of robots. These days, robots with manipulators are lack of ability to detect friction force accurately, so they are difficult to manipulate small objects or perform in-hand manipulation. So we proposed a vision-based tactile sensor that is inexpensive, 3D shaped, and has high resolution of force and position sensing. Researchers have been working on this topic, but traditional sensors such has small resolution, and 2D shaped vision-based sensor has their limitation because of their flat surface, and 3D shaped sensors like OmniTact are too expensive to deploy on the robot manipulation task. So we proposed a high-resolution and 3D shaped tactile sensor that can sense normal and shear force on soft surface. We are now working on to collect a data set to train a network for tactile sensor, and we will train a network to get the force and position information from the resized image data of the tactile sensor. Thank you.
Hi, my name is Misha Laskin, and I'll be presenting a framework for efficient robotic manipulation, a project that was co-led by Albert Jan and Philip Zhao and was submitted to ICA. In this project, we look at the following problem. Though reinforcement learning can learn robotic skills directly from pixels, it's very data inefficient, requires many hours or days of training to work. For this reason, we propose a framework for efficient robotic manipulation. You collect 10 human demonstrations, which takes 10 minutes. You initialize your convolutional encoder with contrastive retraining, which takes a minute, and then you continue training the robot with data-augmented RL, which takes on average 30 minutes. The robotic setup is simple and quite general. You need one robotic arm, cameras for pixel-based input, and a sparse reward. That's it. We see that our method is able to solve 6 diverse tasks in an average of 30 minutes, with a 97% success rate, and this is again purely from pixels. Our method also uses the same hyperparameters across all these environments. Thank you, and for more information, check out this website.
Hi everyone, today I want to talk about an approach that learns a robot policy from imperfect demonstrations of different dynamics. Imagine you have a robot that wants to learn how to play basketball. We can always learn from professional basketball players, but it is often difficult to obtain large amounts of expert demonstrations. Instead, we sometimes have access to data from other professional sports like handball, or access to records of non-professional players like teenagers playing basketball. Our goal is to develop an imitation learning algorithm that learns from a mixture of suboptimal demonstrations and demonstrations from agents with different dynamics. Our method uses a feasibility score that indicates the likelihood of a trajectory being achievable, as well as an optimality score to assess the quality of each demonstration. Our algorithm outperforms our baselines in the retrieval environment in Mykel, and outperforms baselines that only consider feasibility or optimality on a robotic task. In summary, our approach learns from suboptimal demonstrations with varying dynamics.
Hi everyone, I'm Jun, and I would like to share our recent work about aerial manipulation, where a drone is carrying a cable suspended payload. The path planning problem is difficult for this system since it's not only highly dynamic but also hybrid, as the cable could be total slack. In this paper, we provide a novel equivalent model to capture this nonlinear dynamics and hybrid modes together, and use this model for the trajectory generation. Our contribution could be summarized in three parts. Firstly, we provide an equivalent flatness-based model as the drone payload system is differential flat. Secondly, based on this model, we formulate a direct collocation for the path planning where complementarity constraints are considered for the cable tension. This allows us to optimize the trajectory without predefining the hybrid mode switch, and the optimization becomes much faster than the state of art. Certainly, the drone payload system is considered as a polytope, and sign distance constraints are formulated with respect to other obstacles. This formulation of obstacle avoidance allows us to generate aggressive maneuver, such as passing through a narrow window using aggressive payload swing.
Hello everyone, my name is Sophia Williams and I'm a PhD student in Allison Okamura's Charm Lab at Stanford. Haptic devices have enabled us to experience the sense of touch in virtual environments. Traditional haptic devices have been desktop mounted, inhibiting movement. Recent research has begun to explore wearable devices, enabling users to move around and explore their environments. We are developing a mesoscale robotic device that uses layered manufacturing techniques like those seen in circuit design. The device is a lightweight and portable fingertip-mounted haptic device that aims to create more realistic touch by providing normal, shear, and torsional feedback to the fingertips. The fabrication process allows for creating complex haptic technologies at low cost. Additionally, the origami fabrication process allows for incorporating sensing technology or embedded linkages. Please visit our Slack channel to learn more.
Hello everyone, my name is Minho Wang. We shortly introduce our work on efficiently calibrating cable-driven surgical robots. Cable-driven actuation makes inaccuracy due to uncertainty in cabling effect, such as friction and hysteresis, which hinders surgical task automation. To solve this problem, we use the combinations of depth sensing, 3D printable fiducials, and dim learning. We estimate 6 joint angles from fiducial pairs, collect motion data from predefined trajectory, and train a model using recurrent neural network. As a result, we could reduce the positioning accuracy from about 3 mm to less than 1 mm. In automating surgical packet transfer tasks, we achieved a success rate of 96.7%. Please feel free to contact us and visit our website for more information.
Our new work studies the problem of interaction between robots and other non-stationary agents such as humans. Our key insight is that robots can capture the behavior of other agents with low-dimensional representations that change over time. We introduce a reinforcement learning-based framework called Lily for handling these multi-agent interactions. Lily learns to model the high-level latent strategies of other agents and policies for responding to these strategies. By optimizing for its own long-term rewards across interactions, the robot can even learn to influence the future strategies of other agents. We evaluate our method in a real-world air hockey game played between two robots. Naive RL agents such as Soft Actor Critic don't model how their opponent changes and so fails to adapt to the other agent. In contrast, the Lily agent can correctly predict where the opponent will fire its shots, achieving a final success rate of 90%.
Hi, this is Monimai from UC Berkeley, and I'm going to talk about our work on learning to solve complex tasks using hierarchy, data, and physics-based models. We focus on the specific task of solving the physics-based game Bubble Ball. The goal is to get the ball to the finished position, and all the placed blocks follow the laws of physics. This is a challenging problem due to the shown reasons. Only data-driven approaches for this may not be data efficient and generalizable. On the other hand, building models with unknown parameters and under complex contact dynamics is hard. So for our solution, we exploit model hierarchy. A simple point model plans a guide path and then blocks are placed only in local regions. These blocks then use low-level prediction models derived from kinematics and dynamics. The key principles are summarized here. Note that we update the learned low-level kinematic and dynamic models of the blocks after each trial of the game. With this algorithm, we have now solved more than 10 levels with various complexity, and that too with a reasonable number of trials. Thank you so much.
Hello, my name is Shivani, and I work with Professor Monroe Kennedy at the Stanford Arm Lab. Active upper limb prostheses are typically controlled by muscle activations from the residual limb. Since very few muscles control many degrees of freedom, these devices are extremely difficult to operate. We propose that rather than relying purely upon explicit inputs from the wearer, the device should use information from computer vision, augmented reality, and gaze tracking, together with a high-level understanding of sequential tasks to autonomously estimate the wearer's intention. Our approach is based upon recognizing that the wearer's behavior, such as their muscle activations and even their gaze, are a product of their intentions, and their intentions in turn depend upon the states of the environment and the arm, both of which we can measure. By modeling the way in which states influence intentions and intentions influence behaviors, we hope to be able to predict the actions that the wearer intends for the arm to perform. We're excited to discuss further on Slack. Thank you for listening.
We present a sampling-based motion planner for multicopters that can exploit collisions. The planner takes advantage of the fast motion primitive generation and collision detection for multicopters. The method is built upon the basis of the RT-style algorithm and generates collision states by detecting potential intersections between motion primitives and obstacles, and use these states to form collision-inclusive trajectories. Allowing collision helps improve the performance of the sampling-based planner in narrow spaces like tunnels. Since sample states are not discarded due to collisions, the collision-inclusive planner can add samples to the exploring tree more rapidly. We verify the planner by tracking trajectories it generates with our collision-resilient tensegrity multicopter. The collision-inclusive planner allows the system to find a trajectory more quickly, and the resulting trajectory exploits the environment for a change in momentum rather than requiring large thrust inputs. Thank you very much.
Hello everyone, this work is about robust GPS vision localization via integrity-driven landmark attention. GPS vision localization in urban areas is susceptible to multiple measurement faults. Inspired by the cognitive attention in humans, we developed an integrity-driven landmark attention technique in short known as ILA. For each landmark among the available GPS satellites and visual features, our objective is to estimate a binary decision of its inclusion or exclusion. In this work, we jointly maximize the number of included landmarks and minimize the associated position error bound. Our cost formulation is based on stochastic reachability, which is a popular formal verification method designed for stochastic systems. For an urban dataset, we validated that our ILA technique indicated by blue line shows a high position accuracy with a maximum error of only 6.6 meters. Thank you, and for more details, check out our poster.
Hello, my name is Marco Carmona, and today I'll be presenting a neural network approach to switching among an array of stochastic controllers. Below you see 4 images depicting a scene where we see a tricycle reversing and adjusting to then be able to move forward towards its intended goal, the gate. To achieve this, we use a front-wheel drive bicycle kinematic model and a stochastic revolving gate. Here I'd like to point out that the bicycle's velocity could be as low as v1, as high as vq, or could reverse with the velocity of minus v1. To navigate forward towards the gate, we compute the fixed velocity times stochastic optimal controller. And with these computations, we store them in lookup tables for each controller I. To be able to go forward or backward, we use the lookup tables to train the neural network, returning a switching velocity controller.
Hi, I'm Aris Krimsky from the Stanford University Biomechatronics Lab, and I'd like to introduce a new tool I've been working on called CORDS, which stands for Convex Optimal Robot Drive Selection. CORDS is a tool which can be used for optimal motor gearbox selection for problems involving minimum power consumption, minimum mass, optimal parallel spring stiffness, maximum robot runtime, and many more. CORDS optimizes over a database of commercially available motors and gearboxes, which can be found here. So you as the robot designer don't need to spend time poring over datasheets that look like this, or this, or this. We haven't posted the source code for CORDS on GitHub just yet because we are still testing and writing up some documentation, but feel free to reach out if you want to beta test, and also feel free to check out the motor gearbox database that we've posted on GitHub. Thank you.
Hi, I'm Andrea, and I'm talking about rethinking probabilistic models of human behavior. When robots interact with humans, they need models of human behavior for inferring or predicting what people will do. For example, if a person is trying to teach the robot to place the cup on the table, we could assume there are 2 equally good trajectories, left or right. If we add 2 more equally good trajectories on the right, the commonly used Boltzmann model would predict equal probability for all of them. But should it? We essentially still have a choice between left or right. So should adding similar options to the right really be reducing the prediction that you will choose left by that much? In the real world, this problem is even worse because now all options are more or less similar to one another. We rethink the Boltzmann model for continuous trajectory spaces and account for how similarity in their trajectories should influence their probability. While Boltzmann models that humans pick trajectories proportional to their exponentiated reward, we adjust this probability by the similarity between the trajectory and its alternatives. Thank you.
Hello everyone, my name is Akshay Shetty and I work with Professor Grace Gao at NavLab at Stanford University. Trajectory planning for robots typically involves considering a group of candidate trajectories and finding the optimal collision-free one. In order to check that a candidate trajectory is collision-free, a commonly used verification tool is reachability analysis. Previous reachability works compute reachable sets while accounting for robot motion uncertainties. We build on these works in our reachability analysis to additionally account for stochastic and bounded sensing uncertainties. We then design a size metric to compare reachable sets along candidate trajectories in a planning framework. Finally, we demonstrate applicability of the trajectory planner for fixed-wing UAVs in presence of GNSS multipath uncertainties in a shared urban airspace. For more details, feel free to check out our papers and to stop by our Slack channel. Thank you.
Okay, we are live again.
Right.
Okay, we are live again.
Oh, I had my YouTube on. 1 sec. So yes, that was a good first session. A little bit of hiccups, but that was fun hearing from all faculty and the spotlight talks, all awesome talks. So if you guys are interested in hearing more about the student talks or faculty's work and all that, our Slack channel is up. So please go and check that out. We have a break until 10 a.m. So we'll be back at 10 a.m. with the next set of faculty talks at 10 to 11 a.m. Have the next set of spotlight talks 11 to 11:30, and then we'll have our keynote 11:30 to 12. So take a good break, and we'll see you guys all at 10 a.m. again.
Now we are live.
I can see Mark. We are live. Okay. All right. Hi, everyone. Welcome again. If you're just joining us now, this is BARS, Bay Area Robotics Symposium, and we're going to have our second set of talks right now. So the plan is 10 to 11. We're going to have second set of faculty talks, then we'll have spotlight talks, then we'll have our keynote. All right. So in these set of talks, I'm moderating, and the first speaker is Grace Gao from Stanford. So really excited to have you, Grace. Do you want to share screen in?
Yeah, sure. Good morning, everyone. I'm Grace Gao from Stanford University. Today, I'm going to talk about safe localization and navigation under uncertainty for autonomous vehicles. Autonomous vehicles often operate in complex environments with various sensing uncertainties. For example, GPS signals can be blocked or reflected by buildings, creating bias uncertainty due to multipath effects. Additionally, camera sensor measurements are susceptible to lighting conditions and yield poor vision performance in environments which lack distinguishing features. In this example, the LiDAR sensors may have multimodal uncertainty. And then on the other hand, there can be processing uncertainties. For example, if we use a deep neural network to process the vision-based navigation, there can be uncertainties in the network weights themselves. Furthermore, there can be fusion uncertainty because of the uncertainty in individual sensor uncertainties. So for our research, we aim to provide localization, navigation, uncertainty, and resilience to errors of safety, and resilience to errors and uncertainties using machine learning, advanced signal processing, and formal verification methods. And today I'm going to show you some brief examples. For verifiable, so for verifiable perception and navigation, we want to answer the question, how to safely plan vehicle paths with sensing uncertainty. We not only want to monitor the sensing uncertainties, but also predict the characteristics of these uncertainties based on vehicle dynamics, as well as environmental information, such as 3D maps. We apply formal methods such as stochastic reachability analysis to provide provable navigation safety guarantees. In this project of trajectory planning under bias sensing uncertainties, we account for both motion uncertainty as well as bias sensing uncertainty. We enclose the uncertain GPS multipath biases by a probabilistic zonotop. So in the simulation here, if we do not consider the bias sensing uncertainty, out of 100 trajectories, there can be 36 collisions. However, if we do consider the sensing uncertainty biases, our algorithm is able to predict a state uncertainty and then thus lead to probabilistic safe planning paths. So that was for a single sensor. How about for sensor fusion? And then we know that there can be a variety of sensors available to autonomous vehicles, such as LiDAR, camera, GPS, inertial sensors. Can we really say the more the merrier? In fact, including more sensor information can introduce more sensing failures. It can also increase the required computation time, which is a precious commodity in real-time autonomous navigation applications. We aim to intelligently fuse sensing information in order to achieve high integrity and quantified confidence for autonomous navigation. We use graph theory to not only model visual landmarks, but also consider GPS satellites as landmarks as well, and fuse the visual and GPS sensor measurements in a connected graph. We also use an integrity-driven approach to only select a subset of reliable visual landmarks that also form good geometry. Beyond just one vehicle, in the future, when all these self-driving cars and UAVs, when they can operate in a way that they can collaborate together, can we take advantage of the connected and collaborative vehicles for safety? So we aim to leverage the abundant sensing information exchange. Oops, sorry. And we want to leverage the abundant sensing information and then to improve the localization, robustness, and safety. For example, for UAVs flying above tall buildings, they will have open sky views and then ideal signal reception. Such a UAV can serve as a pseudo GPS satellite to relay the healthy GPS signals to vehicles near the ground with poor GPS reception and wrong signal measurements. We can also use graph theory and distributed algorithms to achieve more robust and tech-resilient localization solutions.
15 seconds.
Okay, the last example is on deep learning. We know deep learning is a powerful tool, but it can be also like a black box. So we aim to provide the trustworthiness and robustness alongside the deep learning approaches by training the deep learning network to learn the sensing uncertainties and by utilizing deep learning as additional sensing processing tool. Okay, hope I'm on time. Thank you. Right. So here are some of our research experimental platforms.
All right. So awesome. Okay, so let's see if there are any questions. So I think I have a question from YouTube. So do you have a sense of what a better way is to parameterize noise of these sensors? So like GPS and LiDAR, and it better than treating them as Gaussian. So is there a better way of treating these types of noise?
Yeah, exactly. You know, for GPS measurements, we consider this biased sensing uncertainties instead of a zero mean. And then for LiDAR or vision measurements, we can model them as a multi-modal Gaussian instead of single model Gaussian. And what's more, we can also use a deep learning approaches to learn the uncertainty and then the characteristics of the uncertainties.
Mm-hmm. Cool. Any other questions? I can actually ask a question. So do you also consider like various types of attacks here and how you differentiate between attacks and uncertainty? So there's like these types of attacks, like noise attacks, right? When you add like noise and slowly like tries to like get your system out of the right region. So have you considered kind of like how you differentiate between?
Yeah, we have done quite a lot, and we also participate in quite a few field tests under like a real-time, like a realistic attacks. And then there are multiple approaches. For example, you can leverage the characteristics of the application itself. Take an example of a GPS spoofing attack. You know, the attackers are often like near the ground. It's hard to have an attacker to launch satellites in the medium Earth orbits, right? So you can differentiate by seeing, attacks near the ground or the logistic signals are more likely coming from the sky. And then you can also think about, in the Earth, for example, San Francisco versus New York, if they see the same GPS satellites in view, and then that legitimate satellite, right, it can cover both San Francisco and New York, versus attacker will be really hard for the same attacker to attack both sides.
Okay, all right, great. Thanks a lot, Grace.
Thank you.
Our next speaker is going to be our own Mark Mueller. So Mark, can you share a screen? And Mark is from UC Berkeley.
Thank you, Dorsa. Can you just confirm you can see my screen okay?
Yes.
Excellent. Okay, good morning, everyone, again. I want to talk a little bit about some of our work where we're interested in sort of pushing aerial robots to more extreme environments. I want to talk about two specific sort of results that we're working on that I'm quite excited about. And sort of the motivation here is, how do I get my robot to operate in really extreme unstructured environments at a high rate, so high tempos? And something like, finding someone in a wildfire might be a good motivating problem. And generally in robotics, well, I mean, to do something like this, the big thing you're worried about is your robot colliding with the environment. And there's two things you can do, right? So either you can avoid colliding, or you can sort of embrace the fact that you're going to collide. And I want to talk about these two sort of things that we've been doing that go in these directions. And of course, eventually you'd want to combine these, right? So you want to have the best of both worlds. So as far as avoiding collisions go, usually when we think about robots and how we operate them in such uncertain, unstructured environments, is we take the sensor data from the robot, We build a map using this, and then we have some sort of global planner that runs on the map, and then we have our low-level control that runs using this. And I like to think of this as sort of like LQG control, but at a higher level, where you have an optimal mapping routine, you have an optimal planning routine, and they meet at this interface of the map, which would have been analogous to the Kalman filter estimate. And of course, we know that this makes it easy to reason about optimality, but there are concerns about robustness. And in practice, this kind of implementation is computationally very expensive. So one of the things we're excited about is thinking about, how do I make very fast, very reactive local planners? And the idea is that I want this to be a memoryless object. So rather than building a complicated global map, I'd rather have a local map that I plan in. And it's OK if this local map is noisy, because I'm going to throw it away soon. And then I can do sort of an MPC-like replanning. And this gives us a much faster inner loop that uses this local planning. And of course, you will still need someone that tells your inner loop sort of where to go. But the idea is this outer loop can be much slower, and potentially then we can build in some more robustness because it is slow and it's not mission critical. If there is a failure, we can replan this without losing the vehicle. And for our vehicles, so we're interested in these flying vehicles. I just want to show you some of what I mean by sort of fast planning. Here we have a vehicle. At this point, we're totally cheating with the sensing. This is using motion capture. But this is a quadcopter flying a circle. And then what we're doing is we're lifting up, and we here, I'm using a little broadly, this is Nathan Bucky. He's lifting up this big sheet to block the vehicle, to stop the vehicle in its track. And of course, this is something that's really hard to predict because you don't know when this obstacle is going to appear. So you need to respond in real time. And we use these really inexpensive motion primitives to actually plan for this. And what we can now do is we can combine this idea of the inexpensive primitives connected to an onboard sensor. In this case, we're using depth camera to very quickly plan on the vehicle. And the nice thing is each depth image is effectively a local map that we can plan in. We plan in this local map, we execute a little bit of this, and then we throw away the plan, get a new depth image, and replan, etc. And this should give you a very robust, very reactive planning approach. And there's some computational tricks, which I'm not going to go into, but basically exploiting the structure of the vehicle dynamics and exploiting the structures of the sensor, we can actually run this in real time on relatively limited hardware. In this case, we're using an Odroid to run this on the vehicle itself. Just to show you what this might look like, this is a simulation, just because this has some really nice video that Nathan made, where we see the vehicle operating, and you can see the planning basically takes the depth image, we partition it into these pyramids, and then we plan in the pyramids. And the idea here is that a depth camera, any depth image, is sort of, you can imagine, you can draw these collision-free pyramids with the apex at the vehicle and plan in these. And this allows us then to fly. This is the vehicle flying through an underground tunnel, and sort of in real time sort of plan for these motions, react to unexpected behavior, etc., in this model predictive control-like fashion. This is something we're pursuing at the moment, also pushing it outdoors in a collaboration with the Army Research Laboratory. I realized I don't have a nice video of the outdoors yet, but hopefully soon we can share a cool video of flying through some trees as well. But here we see just what this might look like. And of course, the idea here is that because we're doing this in a memoryless fashion, if your map changes, if someone walks into the room, etc., it very naturally takes care of this because it's replanning continuously from the fresh depth image as you get it. On the other hand, if you allow yourself to collide, what can you do then? And of course, collisions are bad because they break things. So the big challenge is how do you make a robot that can survive collisions, and especially collisions at high speed? And we've been sort of pursuing this idea of a tensegrity cage. Tensegrities are these really interesting ways of designing structures. We either have beams that are purely in compression, or you have these tensile members which are purely in tension. And the nice thing here is when you collide with an obstacle, all of the force should be transmitted either as compression along the beam or as tension along the rope, but there should be no bending moments, which is usually where we have the failures that happen. Now, doing this, we can have this vehicle collide with the wall. This is a big concrete wall in our lab space, and it's colliding here, I think, about 7 meters per second, and it's surviving this collision without too much problems. So this suddenly gives us a vehicle that we can now collide with obstacles with, and we can exploit these collisions. And of course, a nice property of this tensegrity cage is that it is roughly spherical. So if you do collide and you crash into the ground, the vehicle can right itself pretty easily and then continue operating. And just sort of to show you that here, This is work primarily led by Clark. I think Clark is already active on the Slack, and he presented earlier in the spotlight. So hopefully, if you have more questions, you can also chat to Clark. But at this point, we're also working. So now that we have the system, we know that we can collide with obstacles. Now we're starting to exploit these collisions. So can we use the collisions to, for example, discover what the world looks like? Can we use these collisions to fly faster trajectories? Using the environment, for example, to give us momentum changes rather than using our actuators. And then just a big thank you to, of course, all of the people that do the hard work. You see the students listed here. We have, I guess, a special shout out to Jay, who is a postdoc we have, who due to COVID is currently working remotely from Korea on this stuff. But yeah, so the students doing, as usual, all the hard work. And thank you for your time.
Okay, thank you, Mark. All right, so any questions from our faculty audience, from YouTube channel?
I have a quick question.
Yeah, Ricardo.
Mark, great talk. I love the collisions. Do you model them in your planning?
We try to model the collisions. It's quite difficult to model them well. One of the big challenges with the structure is, I think there are, let me think about this. There are 12 points where you could have the collision. Neglecting the unlikely case of hitting with two of the points simultaneously. And the challenge is that, there's a relatively small angle difference that gives you different points of contact. And of course, that gives you very different behavior. So if you model this as a perfect sphere, it would be much easier to model the collision. So we are having quite a bit of trouble predicting, for example, the state of the vehicle after the impact accurately because of small state errors leading to relatively large post-impact collision. And of course, there's just the fact that this tensegrity structure has sort of very different stiffness depending on how you touch it, depending on which members are being affected how. So the collision modeling, we're trying to, but it is difficult to do it accurately.
All right. So one other quick question. Actually, we are running a little bit out of time, but do you have a question mark on YouTube that you should get back to?
Okay, I'll get onto YouTube.
All right.
Let the next person
good.
speak.
Okay, so our next speaker is Dejan Milutinovic. So Dejan, do you want to share your screen? Okay. And he's from UC Santa Cruz. Oh, you're muted. You're muted.
Okay, can you hear me?
Yes, yeah.
Okay, good. Well, I'm Dejan Milutinovic. I'm professor at University of California, Santa Cruz. And thank you for inviting me to speak at this meeting. Today I'm going to speak about composition of stochastic controllers. But before I go on the main topic of my talk, I just want to show you some recent results that I got in collaboration with Professor Werner from UC Santa Cruz, where we are working on some proprioceptive feedback controlled soft finger, and we kind of get like a nice result with it. Okay, so the main topic of my talk is about stochastic controllers and how we can do composition of stochastic controllers to get something meaningful for robotics applications. And before I go into more details, I'll want to say something about an approach that I'm using for a number of years, and in which I'm using stochastic controllers. And I want to kind of convey the message about how we think about stochastic control and uncertainty and navigation. So here is the small chart here saying, like, if our vehicle goes in some unknown environment, which is uncertain, what we do actually say, well, let's model that uncertainty, unknown things, using some sort of a quantitative model. And a good model, mathematical description for that uncertainty is to use stochastic models. So in this small diagram, I just illustrated how this approach works. For example, if you want to follow, if you have a target, let's say a vehicle that you want to follow, and you want to follow by an unmanned area vehicle, which we model as a Dubin's vehicle, originally, like if you want to follow this, solve this problem, you may want to know what is the motion of the target, so that you can plan accordingly the trajectory of this small vehicle. However, if I don't know what is the motion of the target, then what we can do, we can assume, for example, that the target moves like a Brownian particle. So given this prior on a motion about like a next time interval, basically there is a cone of probabilities that is defined based on this prior, which models our uncertainty about how this target moves. And then we do a stochastic control to anticipate that uncertainty. The benefit of doing that way, first of all, here are the results, how you can follow the Brownian particle. We actually can show you the distribution of our distances and everything. The benefit of this is that you compute one controller for a Brownian particle, and that controller is robust to follow other type of the trajectory, which I'm trying to start, but for some reason, just movie doesn't work in this case. But here was like a straight line trajectory, and the UAV will follow that straight line trajectory, and here will be like a more complex trajectory, and the UAV will follow that more complex trajectory. Okay, so then the question is that can these solutions can be used for something else? We all know that when it comes to the stochastic control problem and optimal solutions, we are facing this problem, of course, of dimensionality. So we think if we can somehow have like a big problem and divide in pieces, and then each of the pieces solved by a stochastic controller and then somehow put together, that is basically a project that we are pursuing for already like at least 5 years. So here I want to show you results in which actually we take the circumnavigation controller from these results and combine with the PI controller for velocity of the UAV. And when we do that, we can achieve so-called a formation flight, which is which you see here. And basically, so this is like a stochastic controller, and on top of that is the velocity controller. The controller is robust, so basically a leader, in this case blue aircraft, basically can follow any sort of trajectory, and soon you're going to see it. Like here we commanded the tracking of the blue target from the right and from the left. And this point, for example, very soon, what will happen is that the blue agent gonna turn
15 seconds.
How much?
15 seconds.
Okay. and then you know the red agent will come back to the blue one. So you know that is the other type of result that we have is that actually like an solution for the problem in which the agent should chase other agents and simultaneously avoid them. All our controllers are in the lookup table, super fast, super quick, and finally there are like results where we actually also solve some sort of an assignment problem, also in real time, using a so-called Markov inequality that helps us to do a real-time decision making with the switching of the possible assignments on how we want to inspect some ground objects. And finally, we implemented this also on like when in the problem of combining a stochastic controller, we also planning to implement, and we have some preliminary results on like on the navigation of like a ground vehicle, like a small tricycle, in which we in which the switching and composition of stochastic controller is done by neural networks. So I hope I'm on time.
Okay, thank you so much.
Yeah, thank you. Yeah.
All right, any questions from our faculty, speakers here, or on YouTube? So there is a question, and that is from Sydney, who's asking, how sensitive is the algorithm performance to the accuracy of the stochastic model for target tracking?
Well, that's a very good question. What we actually do, we usually, when we set up a prior, we usually make sure that let's say if it's a Bayesian particle prior, we basically look at what is the mean value, what is the displacement per time. So kind of to figure out what is the average velocity, average displacements, so that we can actually address some realistic, But as far as, from our experience, as far as our stochastic prior kind of covers the possible outcomes in probability sense, yeah, these things work, as supposed to work.
All right. Okay. Thank you so much, Dejan. Okay, so our next speaker is Anca Dragan from Berkeley. So Anca, can you share your screen? Maybe Dejan.
I can't. Dejan has to stop sharing his screen.
Yeah.
Awesome. Hi, everybody. And to Dorsa and Mar for organizing this. Okay, so I wanted to talk a little bit to you today about a theme called goal agnostic assistance that I've been working on in collaboration with these students and collaborators. And I'll just focus on one example today. So we're interested in getting robots to assist people in a variety of tasks: assisted navigation for people with visual impairments, assisting people control vehicles with difficult dynamics, assisting people with motor impairments do things like gaze-based typing, and so on and so forth. And in these tasks, users have a policy that sort of maps states to actions that they take. And then we assist them typically by using these actions to infer their goal and then take actions on their behalf that better achieve the goal. And the challenge with doing this is that people often take these very noisy suboptimal actions that make it kind of really hard to figure out what their goal is. Like in the lunar lander, they overshoot the goal to the left or to the right. And then on top of that, even if you infer the correct goal, we're kind of taking away the person's autonomy by completing the task for them and kind of totally overriding their input. And so we've been wondering lately, could we, instead of correcting the user's actions to make them optimal, could we somehow enable users to take better actions themselves, to decide on better actions? Could we go from sort of this override that we do at the end to somehow the user being able to act optimally and achieve their goal on their own? And so to answer this, we have to ask ourselves, well, why are users taking suboptimal actions in the first place? What's going on there? And one answer that we came up with is that they don't get to see the state of the world, as this diagram would deceptively indicate. They just merely get sensory input, observations, OT, and they're acting based on their belief about the state of the world, which could be wrong, thereby leading them to take the wrong actions. And this happens for a number of reasons, like people can't pay attention to many different sensors at the same time. There are lens distortions causing users to overestimate distance to objects. And we know these are issues because otherwise optical illusions wouldn't be a thing. And so if we want them to take better, closer to optimal actions, then our idea is that instead of correcting their actions, we should see if we can correct their beliefs about the state. And that in turn then enables them to take better actions. And now the challenge here is that we can't actually incept a belief into the user's head. And so what we can do, what we can alter in many tasks is this observation input that they receive. And the key idea here is that it's the true observations, the actual OT, the full observations, they're not necessarily the most informative about what state people are in, especially when they're processed incorrectly by the user because of the systematic biases that we have as people in our perception. And so we operationalize this insight by using kind of an automated assistant to process the full observation on behalf of the user. And this assistant performs state estimation kind of unencumbered by systematic biases that users might have. Then the assistant provides the user with this kind of modified observation that when processed by the user leads to them having a more accurate belief. And so formally, we try to minimize the KL divergence between the assistant's beliefs and the user's beliefs. So after the assistant processes these true observations, it synthesizes a modified observation that it thinks will make the user believe in the same state as the assistant. And what's hard here is that we don't have access to the user's internal state estimation process. And so what we propose to do in this work is actually learn that from demonstrations of users' actions. And that requires this user model. So we model the likelihood of the user taking a particular action, given a history of observations and actions, by marginalizing out the state. And this involves computing a near optimal policy for the task, which we can do. And then we have this representation, parameterized representation of the user's belief, for example, as a neural network. And those parameters is what we're fitting. So we do a maximum likelihood estimation. We train our model of the user's estimate state estimation process using this maximum likelihood objective over the actions that we observe. Okay, so we applied this to assisting people navigate indoors, sort of. They cannot directly perceive the scene in front of them. So basically looking at the house from a bird's eye view, they're trying to reach some position that's maybe in the middle of their house. And if they think that they're in one corner, but in reality, they're in a different corner, that leads to trouble, that leads to bad actions. And that's what we're trying to fix. And so we have an agent guide that can see the user's egocentric scene, figure out what objects are around, and a default guide which sort of kind of tell you what's around. And you'd update your understanding of where you are based on what the guy says. And maybe that you don't always actually know where you are based on that. And in contrast, what our guide does is it selects these objects that are kind of very informative about where it is that you are. Maybe they're rare, maybe they're only in one place in your house. And this tends to result in this more accurate user beliefs. And as a result, the user taking less time to reach their goal. We also looked at a version of Lunar Lander where we made it difficult to see. We added this horizontal bar to help the user perceive the angle of the lander. And I really like this example because what our system learns to do here is just exaggerate the tilt of the lander to compensate for kind of our apparent inability to correctly estimate the tilt. So by the agent lying to the user about how tilted the lander is, the user ends up actually performing better at the task. So I thought that was really cool. Okay, so we've been getting kind of creative with how to enable users to take good actions on their own as a way to assist them. And I think that's a very empowering way to receive assistance. So with that, I'd like to thank you for listening.
Right, thank you, Anca. Okay, so any questions from faculty or from the YouTube channel? I have a quick question, actually. So like this type of paradigm that you're looking at, I think it's very interesting, but do you worry about the type of tasks that you're looking at? Like, for example, Lunar Lander might be pretty reflexive and people might just come up with a few heuristics and don't necessarily like reason about it incorrectly or whatever you want to call it. Like, do you feel like depending on what task they're doing, like different paradigms might be used?
So what's really interesting with Lunar Lander is actually that I don't know that people are actually perceiving the tilt wrong. All that we know is that when you exaggerate the tilt and lie to them about what the tilt is, they take better actions. And it could be that it's something else that explains this, but I thought it is particularly interesting. We also have these navigation tasks. We also have these tasks where there's teleoperation delay and the assistant kind of fixes that. There's sort of many, and I think depending on the task, a different model that you're learning is going to be useful, but it seems like it's always useful to add this flexibility of correcting their beliefs. What might happen is that in some cases actually correcting their beliefs, but I don't have ground truth for that. I don't actually know what their beliefs are. But in some other cases, you're kind of compensating implicitly for something else that is going wrong that we can't actually model. And I thought that was really cool.
That's really interesting. Let me just ask one more question here. So Sid is asking, so to what extent is the guide's behavior ethically problematic? Is this a task-specific problem, like kind of like what I was talking about, or something more general?
Yeah, this is an interesting question. So whenever we do these kinds of interventions, we worry about manipulation, we worry about deception, right? So you can do this to be more informative, but you could also do this to be deceptive. And in particular, you might not be realizing that you're deceptive because if your own state estimation is wrong, right? Then you meaning the agent, if the guy's state estimation is wrong, then it's gonna basically lead the person astray. Now for the task that we're looking at, right, it's very this very basic assistance. You have visually impaired users. You just give them, all that is happening is you filter the objects and give them more informative objects instead of random objects. And it doesn't need to be something that's too wrong with that, but you can definitely take that to the extreme and sort of just make users believe they're in a totally different world than they actually are, and we wouldn't want to do that. So difficult question. I don't really know the answer to. But
all right, thank you, Anca. You have a couple more questions on YouTube, including.
Okay, I'll get on that.
You may want to get to. Okay, so Ricardo. So next speaker is Ricardo Sanfelice from UC Santa Cruz. It would be awesome if you can share your screen.
It's coming in.
Yes.
Perfect.
Hey, welcome.
All right. Well, thanks everyone for organizing this event in the midst of it all. I thought I would start my talk with a short view of our forest, which survived some of the chaos, the fires. I'll be talking about hybrid systems and model predictive control. So it's important that we connect what it means to be a hybrid system. We're looking at systems that have transitions, like those impacts right there to do manipulation. Might have impacts similar to what Mark was showing us earlier, where there is collision between two bodies and you can approximate that's a very rapid change of the system dynamics. We're also interested in conversion systems that switch because transistors are being turned on and off. This is an algorithm that converts power with accuracy that you can control. And we are, over the years, been developing techniques for stability, but more recently we've been looking at ways to do that in an optimal manner. So model predictive control, which many of you know, is a very good framework for design algorithms that are optimal. And the idea is essentially that you have a system, you have the evolution of a system. Let's say that the evolution of the system is over continuous time. And then you predict over some time, and then you pick your best move, essentially. And you execute that for only some time, and then you predict that again, maybe periodically, maybe after some event, and then you compute your input, and then you apply it again, and so on. What you obtain is a very nice optimization-based algorithm that accommodates, because of the problem that is being solved, which is an optimization problem, accommodates constraints, accommodates all sorts of cost functions. And typically what you try to do is to maximize the region of operation, what we call the basin of attraction. And one of the beautiful things, in my opinion, is that you don't need to really write down the expression of the controller. You don't need to write down the dynamics of the controller. It's essentially the solution of our optimization problem, which at the end of the day creates some trouble on how to prove that things work very well. So in this work, essentially what we're trying to do is to solve the optimization problem when you have transitions of the state. This could be logic variables in a hybrid automata. This could be collisions between two bodies. This could be switches in the control algorithm, like the power conversion. And to our surprise, when we started working on this back in 2015, we noticed that there's much about hybrid, but not necessarily about hybrid dynamics in the context of MPC. So we wrote a survey about hybrid MPC and what it means and what are the results out there, and it's a very interesting direction. One of the things that we've been emphasizing is to come up with results, and we're talking about now mathematical results, because the foundation of MPC requires understanding the theoretical properties of essentially the value function. Is how to guarantee that you have always the possibility of continuing solving the optimization problem, maybe again periodically, maybe aperiodically after some events occur, and how do you guarantee stability. And the stability of these systems with jumps is interesting when you have events that might occur consecutively, maybe two switches in the controller occur because a condition in the logic decides to do so. And typically you try to do is to remove what is called Sino behavior, which is arbitrary fast switching. And as I said, we have developed a tool and a framework for solving these model predictive control problems. So if I have time, which I don't, unless Dorsa is giving me 45 more minutes, I will be able to tell you more about the details of how we do hybrid model predictive control. But if you're familiar with hybrid systems, we're typically interested in systems that have transition. This is one of the canonical examples, sample and hold control, where you have physical variables like Z here is the plant state, and then timer that triggers essentially the recomputation of the control signal, and maybe the input is updated after the event and held constant between the event. This is essentially sample and hold control. This gives rise to a family of systems that are hybrid. They're modeled as continuous differential equations and difference equations. This may be set valued because of uncertainty or non-smoothness. And the type of trajectories that you get when you look at this sample and hold problem in particular is essentially a sequence of events that in this case is periodic and creates essentially jumps in the system. Hybrid systems allow to model switch systems and other class of systems, as you probably are familiar with. One of the things that I would like to conclude here is how do we solve the optimization problem? So essentially, we have a way to formulate model predictive control for this type of systems. Essentially, what we have now is a cost functional that depends on the cost during the continuous evolution of the system and also on the cost of the discrete or of the jumps of the system. So we penalize both symmetrically without giving priority to any of this, and everything gets essentially accumulated. So now you can, with this structure, define what you call a prediction horizon, which might be hybrid. Essentially, you have your system that might evolve and might collide, and that collision needs to be predicted in your optimization problem. And you essentially come up with the very complex problem to solve, which is the optimization under constraints problem, which is essentially the holy grail of optimization. So how do we solve this problem? Certainly, there are some technical assumptions that I won't get to, but essentially, if you have a system that is hybrid and you have a set that you want to stabilize using model predictive control type of a strategy, but now with hybrid elements, you need to design your cost functional with stage cost functions for the continuous part and discrete part, which we call flow and jump, with some basic properties for positive definiteness is necessary. And then, as you notice, we are using terminal cost for MPC, and we require the terminal cost function to be what is called a control Lyapunov function. And under these conditions, we are guaranteed that MPC is going to find for us the feedback law numerically that will stabilize the system. In that regard, as you probably expect, how do we solve the optimization problem? Well, there are many ways to do that in the literature for continuous time and discrete time systems. We have some ways to do that for the case of discretized hybrid systems. And that relies essentially on the asymptotic stability property that we are able to prove for our closed loop system using hybrid MPC. We get existence of essentially trajectories of the system, which is critical. In other words, there will be no deadlock for the system. And we also have a stability and the convergence properties that you would like to have. And the tool essentially that we have developed and we're still working on boils down to a script in MATLAB currently that we can run in our systems and execute trajectories by solving the optimization problem as we go forward in time. That's pretty much it. There are a lot of other questions associated to MPC that are open, and I will be very excited to talk to you about. We have run a couple of workshops at the IFAC World Congress Conference and also the CDC over the past 2 years. A lot of open questions about how to solve maximum principles, how to actually discretize efficiently, and how to relax some of the conditions that we have, and certainly a lot of room for improvement here. I want just to throw this out for you and give some references. And there is a book that is about to appear in less than a month at Princeton University Press on hybrid feedback control that touches upon this type of problems. So that's my presentation. Thank you, Dorsa. Back to you.
Ricardo. Thanks. So, all right, so there's a question from Karen who's asking about the robustness of the approach with respect to disturbances. So like, how would the approach change, like when you're adding disturbances and so on?
Right, that's a great question. So this is essentially what happens when you implement this type of approach, right? Receding horizon, essentially at every event, let's say every t seconds, you resolve your problem. This problem start this discretized optimization problem I was talking to you about. If you have some information about the disturbances, then what you can do in your discretization, you can incorporate those into your model. So let me go back to the model slide, which I went kind of far. But essentially, what you do is, where we go? Here. What you do is you have initially a nominal model, like a differential equation without perturbations. This is just control input. So what you do when you solve the optimization problem with disturbances, if you know, then you turn that into a set value problem. Essentially, this map, let's say the reset map, if you are thinking about discrete time systems, you add some perturbation. And that perturbation gives now non-determinism in the system. So if you have that information, you can add it into your model. If you don't have it, the good news is that since you're receiving feedback, you're closing the loop every so often, you're going to be able to compensate. But certainly, if you don't put information about the disturbance in the optimization problem, you won't be able to compensate for something you don't know, most likely. So there is some inherent robustness of MPC that we have, but for large perturbations, that's an open question.
All right, thank you so much, Ricardo. Okay, so let's go to our next speaker. So our next speaker is Hannah Stuart from Berkeley. Hannah, can you share your screen?
Can you see that all right?
Yes, yeah, thank you.
Good. All right, I'm Hannah Stuart. I'm an assistant professor at UC Berkeley in the Mechanical Engineering Department, and I run the Embodied Dexterity group. Now, I've been on a number of different projects, and as you can see, they're really focused on electromechanical design for the point of contact between an agent and the world. And here you can see that there are two different themes. One is focused on humans as the agent, and the other one is focused on robots. Now, there are a wide number of researchers who are extremely talented who contribute to a wide number of projects in the lab. Unfortunately, today I can only focus on two, so I'm going to give one example for the human side of the lab and another example for the robot side of the lab. Let's start with the robot side, and this is work done by graduate student Monica Lee, who is participating with a 1-minute teaser today, and she's a NASA Space Technology Research Fellow. The idea is that it's well known that that friction is a really critical part of grasping. And so you can see here, if you have a very slippery object, it gets pushed out of the hand. And this project is looking at what the effect is of a fluid lubrication, be it water or oil or something else, on and how that affects how we design skin and design for friction. Now, robots in underwater environments could be really helpful, for example, for a dishwashing robot or a machine that's going into the ocean. And for these machines, soft skin is a really sensible, easy to integrate technology. They can also distribute contact stresses if you're handling fragile objects. But prior studies that look at the effect of fluid lubrication on soft skin contact really focus on microscale features. In this work, we wanted to look at larger features at the milliscale, closer to what you see on a pruny fingertip after you've been in the bath for too long. So we took a number of different skin designs with these larger features with a wide variety of stiffnesses, because stiffness is well known to affect our contact friction. And we applied this to fingertips in wet conditions. And what I want to point out here is first, the general trend from left to right. As our skin is getting stiffer, we see an overall increase in our kinetic friction. And again, that's a well-known property. What we were asking is, well, when does fluid lubrication start to have a really dramatic effect? And what we see is on the far right side, the most important effect. On the blue line, which is in lubrication, we have this big drop in friction from only 3 contacts to 1 contact. And that is where our lubrication is most important. So what we take away from this is that if we want to have a skin that's going to maximize our friction for a dishwashing robot, maybe we want to have just a few features, which is quite not typical from what I see in terms of how people design soft skin. And so while this is kind of a simple technology, it's one that we should very carefully consider as we're designing robots for more slippery situations. Now, in the process of doing this work, we've also developed a new method for visualizing real contact, which can differ quite dramatically from what we would expect our contact to be, and doing this visualization in lubricated conditions. So here we're using frustrated total internal reflection, now with a dyed lubricant to visualize this. And this will be a really important tool as we push forward our understanding as to why these effects are most apparent and when. So if you're interested in learning more, please check out our RA Letters paper. Now I'm going to quickly fly through this exoskeleton that a number of students have worked on, and this work is supported by the Hellman Fellows Fund. Now, exoskeletons designed for people with spinal cord injury often rely on coupling wrist and finger motion. And doing this end effector coupling can really dramatically decrease your ability to use the full workspace of your arms. And so this device uses sort of a clever kinematic inversion to have both the person controlling the grasper as well as a motor, and they can both operate at the same time. Which lends itself to really interesting behaviors, like allowing a person to just maintain their grasp regardless of the pose of their wrist. And so this is a really fun and interesting test bed for us to start studying brand new questions in terms of partnerships between machines and people, including the kinesthetic effect that you maintain by allowing the person to still remain in control. So that's a brief overview of two papers. I encourage you to take a look at them. But there are, of course, a lot of different other projects, so please visit our website. For example, we recently published open source files for the Ocean One hand. So if you're interested in building this hand for ocean exploration, please check out our GitHub page.
All right, thank you, Hannah. Thanks for being exactly on time. All right, so we have a question from Allison. So she's asking that, so in your grasping underwater work, you mentioned kind of this microscope prior work, and also for your current work, you're looking at milliscale. So she's asking, are there ways of looking at macro scale finger shape for doing something?
Yeah, I would say that we call it milliscale, but it's sort of bridging from very small features all the way up to that macro scale. So the flat, smooth skin that we test is actually just if you had smooth skin on your finger with no features at all. So it is actually already sort of bridging that. And I would almost say that it is that macro scale that we're finding to be really critical, that like just a couple grooves or a couple features can make a really dramatic effect. So yeah, that's a great point. I think we had trouble naming exactly what we were doing in the size scale. Yeah.
Cool. I think that we have time maybe for one more question. So Clark is asking is there analysis on this, which basically answers why this unintuitive phenomena is taking place here?
Sure, yeah, so we've offered a couple simple explanations. So one of them is basically as you're trying to squish plates together, you have to apply more force to squeeze the fluid out. And that effect is really just most pronounced when you're going from a smooth, flat surface to just 3 contacts. But that effect dramatically decreases as you have more contacts. So it really is this thin lubrication film that's contributing. But the details of that, we still need to study. And so that's what the visualization using the FTIR is going to be so important for. Yeah, that's a great question and still an open question.
All right, thank you so much, Hannah. Okay, so our next speaker is Ron Fearing from UC Berkeley. Ron, can you share your screen?
All right, thank you. Okay, do you see my screen okay?
Yes. Yeah.
Okay, great. So I hope the movies are going to play. We'll see what happens. So I'd like to talk to you today about the Salto precision leaping and landing using stance phase balance control. This is really the work of Justin Yim, who just finished his PhD, now doing a postdoc at CMU. But I've kind of like to share with you the results he is. Okay, so this is, as I said, as part of his PhD dissertation. Also acknowledged collaborators Eric Wang, Mark Plechnik, and Duncan Haldane made this possible. So those who are not familiar, this is our Salto robot. It's a monopedal hopper, which is designed to have very high jumping agility. That is the ability to jump, we hope, like things like galagos and squirrels. That is the way we describe it. We have this metric called vertical jumping agility that allows a robot to repeatedly jump. So there's a lot of jumping robots that you could consider a wind-up robot, where it sits for a while, winds up a spring, and then releases that energy and jumps. But we're looking for an agile jumping robot, which is able to do repeated jumps. So think of also things like mountain goats. So our metric comes out to just be meters per second, height gain over the time to apex. So if you go quickly enough, you can go up here like going up a ladder. But one of the important points on this is that originally we developed this metric for climbing obstacles, but it's also very important for landing. So if you want to land precisely, you have to also control the energy in landing and to allow you to do the next jump if you want to maintain precision. So the underlying mechanics of the system is using a series elastic mechanism combined with power modulation, which is inspired by the kinematics of an animal like Galago, where there's a combination of energy production for the muscle with energy storage in the tendon that can be released rapidly, which gives rise to a high jumping agility and ability to do things like literally jumping off the wall. So you haven't seen this before. Here's our originally got the robot working with jump off the wall. We can repeat that jump. And we have a lot of energy here. And so as I'll address in a moment, one of the issues is that very small errors in anything will give rise to a large change in velocity and a change in final position. So we have to get a handle on making this precise. You can see there's a lot of scatter there. So we look at first looked at flight phase control from a couple years ago. So just the idea here is, for the moment, ignore this stance phase. It's in stance phase for only 70 milliseconds. It's got a flight phase of about 1 second. So during that flight phase, you can control the attitude using the tail control. And you have some control at the launch time of your velocity by doing a precise leg extension. To give you an idea of the sensitivity here, a 2-degree error will give about a ½ meter per second horizontal velocity error. But by adding in a very precise model and using a deadbeat type control, taking account for all of the modeling errors we could find related to this flight phase control, we can get this error down to less than 10 centimeters, which allows us then to locomote on situations like this. They showed this at bars last year, but this is in a motion capture system, and there's a set of target locations, so it can go up onto the various surfaces without falling off. And this was actually, as you think about the original control, had about a ½ meter circular error probability. So we were very excited to be able to hit something as small as a chair. Well, we can go actually, so we're thinking like, well, we're thinking, what if we wanted something that could jump from branch to branch in a tree? That 10 centimeter error is not really going to be adequate. We need to go to something smaller. So we're looking at a control. This is work with Roy Featherstone, where we're looking at now that 70 millisecond stance phase. We could break that jump into a leaning component and an extension component, treat those controls separately. The balance controller can be handled from, this is Roy Featherstone's model, just a chain of integrators to control leaning, a leg control dealing with the series elastic controlling the launch energy. Combine those two together, and we get a nice, this is beautiful animation from Justin. I don't know how he does it in PowerPoint, but it's great. You can see here the various trajectories. And the point I wanted to make here is that there's a sensitivity depending on your landing angle. So you can plot out the, as you choose different velocities, you get different errors. So let me just show you the results of this. So here is a precise landing. So it just nails the landing, and I won't show that in well, okay, it'll just finish up, show it in great detail, and there it comes down, and it just nails that spot because it's got good control of the energy both for launch and landing. So let me just finish with this slide here. So we're now down with a stance phase balance control, 1.6 centimeters. We are really hoping to be able to nail a branch, and just to inspire us as a squirrel landing on a branch. And we do have Salto with a branch gripper on it, designed by Eric Wang. And hopefully by next year, we'll have a nice video for you showing it salto jumping from branch to branch. Thank you very much.
All right. Thank you, Ron. Okay. Any questions from our faculty or from the YouTube channel? I want to ask a silly question that usually comes up, but just wondering it in this setting. So like in this setting, there is quite a bit of design that goes in here, right? So how do you differentiate which parts of it is about the controllers and which parts of it should be on design, right? Like, and which parts of it should be about learning. So yeah, like I feel like a lot of people like end up doing learning-based approaches, control-based approaches, or design, and like them together are at the end of the day making the system. So for these types of systems, where do you think are the boundaries?
Yeah, so all of the things we've done, there's really no way to decouple those. I mean, when I started out, I thought there would be a nice, okay, give me the system and I'll do the control. But all of these things we're doing, we're using this structure in such critical ways to perform the task that like for example, the series elastic mechanism here, the design is part of the control, and you can't do one without the other. And that might be sort of a fundamental thing. A longer talk on that, but if you want to exploit the maximum performance of the system, it's not like you can put a negative feedback control on it, because your negative feedback, right, you're in a sense taking away energy in some case. So this is, you design the system so it works with the minimum amount of negative control energy to get the best performance.
Mm-hmm. So one more question. So Andy, she is asking, are you able to control the salto in any way after it lifts off?
Oh yeah, so it's got in the picture here, it's got two rotors which control it for the roll and yaw, and it has a inertial tail for pitch. So it's got it does have the ability to reorient itself in during the flight phase.
Cool. All right, so I think we're out of time, but Ron, you have a couple more questions on YouTube. You might want to check them and see.
Okay, thank you.
Okay, all right, thank you so much. So, okay, so I'm going to switch to Erdem now, and we're going to have our spotlight talks.
Thank you.
Hi everyone, my name is Patrick Franks and I am a member of the Stanford Biomechatronics Lab advised by Steve Collins. My research focuses on how lower limb exoskeletons, like the one shown here, can best assist walking. In my research, I've been using a bilateral lower limb exoskeleton that can assist the hips, knees, and ankles simultaneously. This tethered device uses off-board motors to keep worn mass low while giving us large actuation capabilities. To find effective assistance, we used a process called human-in-the-loop optimization, where the control of the exoskeleton is updated in real time based on biomechanical measurements of the user. For 3 users, the exoskeleton reduced the metabolic cost of walking by 50%, showing that at least half of the metabolic energy expended during walking can be saved through exoskeleton assistance. These findings have been consistent for walking at different speeds, grades, and loads, indicating exoskeletons could be massively helpful for walking in varied terrain in the real world.
Hi, my name is Charlotte and I'm a student in UC Berkeley's MPC lab. I'm interested in designing learning controllers that solve tasks in dynamic environments. Our goal is to use data from previous tasks in order to solve the tasks in new environments. For example, if a controller has learned to play early levels of the computer game Flappy Bird, can it also beat future levels? Purely data-driven approaches are often difficult to generalize and guarantee safety in new environments. Purely model-based methods can be provably safe, but require models of every possible environment. I propose a hierarchical approach where high-level strategies are learned from previous task data. Strategies map an environmental forecast to a target set the system should aim for, and can be represented using any data-driven method with probabilistic guarantees, such as Gaussian processes. The target set is used as a terminal set in a low-level MPC. In Flappy Bird, given a forecast of the new location and size of the pipes, the strategy outputs a range of heights for the bird. Compared with the short-sighted MPC controller available online, our approach results in 96% higher average scores. For more information, please check out our paper. Thank you.
Hi everyone, this is Lin Shao. I'm presenting our work called Concept Robot, Learning Manipulation Concepts from Instructions and Human Demonstrations. In this project, we want to endow our robot with the ability to acquire manipulation concepts. These manipulation concepts can be seen as mental representations of verbs in a sentence. Given initial scene images, when we send various instructions, such as put something behind something or put something into something, we want our robot to generate motion trajectories to accomplish these tasks. We use the 20 billion something something dataset as the visual demonstrations and set up 78 tasks in simulation. We apply the learning from demonstration pipeline and train the unified model that will take in various task instructions and scene images as input, and output trajectories for 78 different tasks. Here we show some examples. Our multitask policy can also generalize to novel but similar instructions. For more details, please see our webpage. Thank you.
My name is Ellis Ratner, and today I am presenting our work on efficiently approximating solutions to multiplayer games. This is joint work with David Friedrich-Kyle and Lasse Peters and our advisors Anca Dragan and Claire Tomlin. Many problems in robotics involve multiple decision-making agents where, in order to operate efficiently, each agent must reason about how its decisions will influence the other agents. Differential games provide a natural way to express these types of problems. Unfortunately, many solution techniques are computationally challenging and therefore difficult to apply in real time. To address this, we introduce an approximate solution technique based on iteratively solving a sequence of linear quadratic approximations to the original game until convergence, inspired by ILQR. We show that our algorithm performs well in practice on several simulated examples where the solutions exhibit complex interactive behavior. We also demonstrate our algorithm running in real time on a robot navigating around two other people. Thank you.
Hi, my name is Sydney, and I've been working on generating probabilistic safety guarantees for neural network controllers. Although neural network controllers have been shown to represent expressive control policies, the complex and somewhat unpredictable nature of them makes their performance difficult to verify, and for this reason, their use has been limited in safety-critical applications up to this point. If we want to experience the significant benefits of neural networks in these applications, we need some way to be able to verify their performance. With this motivation in mind, we developed a method that adapts MDP model checking techniques to obtain probabilistic guarantees on properties of neural networks, and apply this method to determine an upper bound on the probability of collision for aircraft collision avoidance neural networks. To ensure that we provide meaningful estimates, we developed techniques to reduce over-approximation error both before and during the model checking process. So if you're interested in learning more about this work, please do not hesitate to reach out with questions.
The main goal of our work is to characterize optimal control laws for discrete end systems with constraints under the presence of disturbances as zero-sum games. When evaluating the cost given a specific input action, computing solutions is undoable in general, and some of those solutions may exceed the constraints set without being able to evolve anymore. Some disturbances under the optimal control action may render a specific set of interests unstable. That's why our approach is based on cost evaluation results with conditions or Lyapunov-like functions. One player assigns the control input that aims to minimize the cost, while the other player assigns the disturbance seeking to maximize it. We characterize the solution of this problem as a feedback loop, and under additional sufficient conditions, we guarantee asymptotic stability of a set of interests without requiring dynamics to be linear, nor the running cost to be quadratic, nor completeness of solutions. Thank you so much.
In this work, we aim to facilitate reinforcement learning by generating tasks. Consider training a robot to push the target object towards a goal in a cluttered tabletop environment. Directly learning to solve such a task from scratch would be challenging. Therefore, we propose AppGen, an approach for progressively generating tasks as curriculum. In our approach, a task generator produces new tasks through a procedural generation module. A task discriminator learns to estimate the similarity between the generated tasks and the target task. The task generator learns to balance the similarity and the reward such that the policy can make efficient progress. AppGen learns to progressively add objects and obstacles in the environment to create similar but easier scenarios. In this way, the policy can efficiently learn to solve the target task.
Hi, I'm Monica with the Embodied Dexterity Group at UC Berkeley. My research focuses on conduct design for underwater applications, such as dishwashing and remote ocean exploration. Soft skin is a common solution because it conforms and distributes contact stresses, and is relatively easy to implement onto existing grippers. We tested soft skin pads with varying surface features and found that having relatively large features increases apparent friction in submerged environments. This indicates that when designing for lubricated contact conditions, robotic fingertips with a few features would exhibit the highest friction, rather than something smooth or finely textured. Additionally, we developed a technique using frustrated total internal affection to image contact area of soft skin pads in lubricated conditions.
In this work, we fielded a team of UAVs to survey a large Adelie penguin colony in Antarctica. Understanding how the populations of penguins and other Antarctic wildlife are changing can help reveal how climate change is affecting their habitats, as well as some downstream effects felt around the world. Our mission was to create a coverage path planning tool that extends to multiple agents, which minimizes the total amount of backtracking, while still adhering to coverage, overlap requirements, and other environmental constraints. If you'd like to know more or just want more penguins in your life, please contact me on the Slack workspace or feel free to email me.
Hi everyone, my name is Abhishek Gupta and I'm here to talk about reset-free reinforcement learning via multitask learning. Reinforcement learning typically relies on the availability of episodic resets. However, these episodic resets can often be hard to provide, requiring significant instrumentation of the environment or human intervention. Instead, we want to be able to learn reset-free, but as shown here on the right, this can often be quite challenging. While learning single-task reset-free can be quite challenging, in many cases, we actually want to solve more than one task simultaneously. And the key question we ask in this work is, can reset-free reinforcement learning actually be easier in this scenario of multitask reinforcement learning? The key idea here is when we're learning multiple different tasks together, we can use some tasks to reset other tasks, thereby making the whole process easier. When considered in the context of dexterous manipulation, let's say we are learning a family of tasks with recentering, reorienting, picking up, and in-hand manipulation. When we look at the training process, it looks something like this. While there are no resets provided, some tasks provide resets for others implicitly. So if the object is in hand and it's dropped, we can try recentering it, reorienting, and then picking up to resume training. We see that the learned behaviors this way are quite successful. Resets were provided, and it does significantly better than a number of baselines, reaching around 75 to 80% success.
Hi, I'm Karen, a PhD student from the Stanford Autonomous Systems Lab directed by Professor Marco Pavone. My research is on developing safe and trustworthy autonomy for safety-critical applications, such as settings where robots are interacting with humans. I am currently working on using signal temporal logic to embed interpretable logical structure into deep neural networks. Signal temporal logic provides a formalism for us to translate natural language into a concise mathematical representation, and I have developed a technique called STLCG, which translate the logical formulas into computation graphs, making it compatible with deep neural networks. So come to the Pavone Lab Slack channel if you're interested in learning how you can make your neural networks more interpretable.
Hi, my name is Eugene Vinitsky, and I'm presenting energy optimization of mixed autonomy traffic at scale. Our goal is to use autonomous vehicles to improve the energy efficiency of a complex, calibrated model of highway traffic. We focus on the I-210 in Los Angeles, shown at the top right, and our model of it built in the traffic simulator Sumo on the bottom right. We introduce shockwaves into the system by placing downstream congestion at the end of the network. By doing so, we get the following time-space diagram, in which the energy-consumptive traffic shockwaves can be seen as the black line sloping downwards to the right. We introduce 5% autonomous vehicle penetration and use multi-agent reinforcement learning to optimize the energy consumption in a fully decentralized fashion. By doing so, we get the following time-space diagram, now shown at the bottom right, in which the traffic shockwaves have been smeared across the network, roughly diminishing their effect on the system. By doing this, we get an improvement in average energy efficiency from 18 miles per gallon to 32 miles per gallon.
Hi, I'm Toki Migimatsu, and I'll be presenting our work on task and motion planning. Task and motion planning, or TAMP for short, gives robots the ability to produce long horizon plans through a combination of symbolic and geometric reasoning. TAMP has shown promise in allowing robots to come up with clever solutions to tasks such as this one here, to place a small box that's outside the robot's workspace on the large box. However, a critical problem of TAMP is that it's computationally expensive, often taking on the order of minutes to compute, making it impractical to use in dynamic environments where objects may be moving. We've reformulated TAMP to optimize trajectories over object-centered Cartesian frames rather than joint configurations of the robot. This means that plans produced by this framework remain valid even if objects are moving. The plans are executed by reactive controllers that adapt to changes in the environment in real time. We also demonstrate this working on a real robot with moving objects in inaccurate perception and control. Please check out our project page for more information. Thank you.
Our work focuses on parameter estimation and system identification for hybrid dynamical systems, which are systems that contain a combination of continuous and discrete time dynamics. Parameter estimation for hybrid systems presents multiple challenges compared to more classical estimation techniques for systems that are purely continuous or discrete. Namely, there are typically multiple sets of dynamics corresponding to the continuous and discrete time dynamics of the system, known as the flow and jump maps, respectively. The sets on which these maps occur may be unknown and are typically functions of the unknown system parameters, and the observability characteristics of the system may change across the flow and jump sets. We propose a solution to the problem of hybrid learning using finite time parameter estimation for systems whose dynamics satisfy a particular form. By imposing a dwell time constraint, finite time parameter estimation permits online determination of the system parameters if the flow and jump sets are known or can be estimated. Please contact me on Slack if you wish to learn more. Thank you.
Hello everyone, my name is Bernard, I'm a PhD student of CISO, and I'll be presenting snippets of my research. First is environment prediction, which is key in developing safe robots, such as AVs, who use occupancy grids based on LiDAR measurements, and doing predictions using mechanisms such as conv-STM. However, such frameworks tend to vanish moving objects. To account for that, we developed a temporal attention mechanism, which enables to recover missing detail as shown below. The prediction architecture is available online, and we're currently developing an open source growth pipeline. Second is effective validation of black box systems, where exhaustive evaluation over the entire dataset is not tractable. We would like to intelligently automate selective validation to maximize the number of failures for our system under test. Here, we extend ideas from adaptive stress testing, teachers doing curriculum learning to develop this framework. Thank you for listening.
Hi, my name is Cynthia, and I work with Professors Dennis Liu and Hannah Stuart at UC Berkeley. Mobility on other planetary bodies is an evolving challenge as rovers attempt to traverse more types of terrain. For example, Mars 2020 will face large step-like fractures in bedrock that are unavoidable and require large drive torques to ascend. Existing suspension design and torque control strategies attempt to minimize the tractive force to normal force ratio at each wheel in order to reduce power and avoid slip, but they typically only consider drive torque as an optimization variable. They have not yet considered optimizing normal force, which could be achieved in a highly dynamic manner using a control moment gyroscope. We show through dynamic models that gyroscopic force redistribution can lower the drive torque requirements and increase margins to slip in order to enable climbing larger obstacles. We are still working to validate this experimentally. CMGs can be powerful actuators in low gravity environments, and we believe that they may be useful within multiple terrain contexts.
Imitation learning is a promising paradigm. A handful of human demonstrations can teach the robot basic skills like pushing. However, it's hard for the robot to generalize beyond demonstrated tasks. In this work, we present a method that enables a robot to generalize to new start and goal combinations from a fixed set of human demonstrations. Consider Task A, where the robot retrieves bread from the container and serves it, and Task B, where the robot places the bread from the table into the oven. We receive demonstrations of each and would like to compose pieces of these demonstrations to enable solving new tasks. For example, moving the bread from the container into the oven. Generalization through imitation, or GTI, is a two-stage algorithm that enables such compositional generalization. We ask the robot to start from the initial state of one task, bread and container, and reach the goal of the other task, which is to put the bread in the oven. We emphasize that the policies perform in closed-loop visual motor control at 20 Hz purely from image observations.
Consider a robot that has been trained using reinforcement learning to take an object out of an open drawer. If the robot is then placed in a scene where the drawer is instead closed, it will likely fail to take the object out, since it has not seen this scenario or initial condition before. How can we learn policies using RL that can generalize to new initial conditions? In this work, we propose to extend skills learned by RL through use of prior datasets. While the task-specific dataset consists of behavior relevant for the task, the prior dataset can consist of a number of random or scripted behaviors being executed in the same environment. If a subset of this prior dataset is useful for extending our skill, we can leverage it for learning a policy that can solve the task from new initial conditions. Crucially, we don't require this prior dataset to be labeled with any kind of explicit rewards. Our method leverages recent advancements in offline reinforcement learning. For more details, come to our Slack channel called Levine Lab or visit the project website. Thank you.
Hi everyone, I'm Simon and I'm working with Zachary Manchester at CMU and Max Schwager at Stanford. Together, we've been combining tools from optimal control and game theory to generate complex interaction behaviors for multi-agent systems. We've applied our methods to autonomous driving problems like ramp merging and intersection crossing. The game theoretic framework allows us to plan the trajectory of the autonomous car and to predict the trajectories of the surrounding vehicles jointly. In this way, we can capture the influence of the autonomous car's decisions on the other vehicles. We've implemented a model predictive controller that solves for Nash equilibrium strategies under state and control input constraints. More recently, we've integrated inverse optimal control to this framework. This allows the autonomous car to estimate online the objective functions of the cars in its surroundings and to reason about uncertainty. Please join us on the Slack workspace for more discussion about these works. Thank you for your attention.
We explore applications of reinforcement learning to large-scale mixed autonomy traffic control tasks. These tasks pose challenges to standard RL techniques, as the influence of individual vehicles' actions on traffic is delayed. And as such, better exploration is required over multiple time steps to learn meaningful control strategies. In order to address this limitation, we studied the application of HRL on these tasks and find that hierarchical reinforcement learning techniques can learn strategies that both improve the throughput or average speed of traffic while reducing the energy consumption of traffic. See our paper below for more. Thank you.
Hi everyone, my name is Robin Brown and I'm a PhD student in the Stanford Autonomous Systems Lab. My research is focused on leveraging locality to design scalable and efficient coordination algorithms for multi-robot systems. Locality essentially is a measure of how well particular problems can be solved using only local information. This is a natural notion for understanding if and how multi-robot networks can operate even when individual robots only have limited views of the network. In my work, I develop metrics of locality for classic problems in multi-robot systems. I then use these metrics to inform the design of coordination algorithms that leverage locality to eliminate excess communication. My goal is to integrate these into an end-to-end framework for analyzing different multi-robot problems and automatically developing algorithms for such problems. If you're interested in learning more about locality and multi-robot systems, please reach out to me through the Pavone Lab Slack channel. Thank you.
Okay, we are live again.
All right.
Can you guys hear me?
Yes, we can hear you. Okay, perfect. Hi again, everyone. Welcome back. So we just finished our first and second set of faculty talks and student spotlights. So for the next session, the next half an hour, we're going to have a keynote by Rodney Brooks. Really excited to have him today. And then after that, we're going to have a third set of faculty talks, and then that will be the end of the program. All right, so with that, let me introduce Rodney Brooks. So I'm really excited to have him today with us as our keynote speaker. He got his PhD at Stanford and he did his postdocs at CMU at MIT. He was a faculty at Stanford and MIT and was directing the MIT AI lab and CSAIL until 2007. Rodney has founded 7 startups, including iRobot and Rethink Robotics, and he's now the CTO of Robust.ai. And he's also writing a book at the moment, which in his words, is a deeply academic book on how AI and neuroscience might still be in their phlogiston phase in a hangover from 1945 to 1965. So with that, I'm really excited to have you with us here today, and welcome.
Thanks very much. Let me share the screen. See if that gets there. Is that there? Yes.
Yes.
Okay. So thanks so much for inviting me. I tried hard not to say any. This is a new talk. All new, no one's seen it. I tried really hard not to be too controversial. And I want to point out beforehand that I was asked to speak about, startups and the difference with academia. So what I'm going to do is contrast academia and startup life. I'm not saying one is better than the other, and academic life and academic problems are real. So when I'm talking about things, I'm really aiming them at startups. And I've got 3 messages today. No, why is that? No. Oh, maybe that. Yeah, 3 messages today. First one is, if you move from academia to startups, prepare to be disappointed, because the time it takes to do things can be very, very long. And the scope of what you can do is not as wide as you tend to think about in academia. It's much more narrow. Second thing is, if you want your research to be used in startups, then make things work in the most outrageously hard environment first. Don't leave that for later, and I'll explain why that's important. And the third thing is, you're gonna have to get over your theorem and formalism envy, particularly around optimality. That doesn't necessarily help much in companies that are deploying stuff in the real world. So there are different reward structures in academia and startups, and that changes the behaviors that you have to have. In academia, being smarter than everyone else is sort of important, or is deemed to be important, whereas in startups, building a great team is important. In academia, you want to, solving an open problem is a great thing to do. You get a great paper, you get a reputation, but in a startup, it's about selling lots of product. In academia, you want high H-index. Although I could quibble that that doesn't measure everything, but you want a high H-index. In startups, you want a high margin. The high margin is to sell one additional incremental copy of your product. What's the percentage of profit on that incremental? What's the margin on that? And in startup land, the more obscene the margins, the better. Google and Facebook have obscene margins, which is why they are valued so highly. And your depth is really important in academia. In startups, it's breadth. So if you want to, get your PhD thesis to a commercial system or any particular paper that you've had in academia, you start off with this brilliant idea, the thesis or the paper, but that's really only 10% of what you need. There's another 90% to make that idea real. And once you've done that 90%, now you've got a robust demo and you can raise products for product development. And then there's another 90% on a much bigger base to turn it into a real product. And guess what? There's another 90% on top of that for manufacturing, marketing, sales, distribution, return, service, sustaining engineering. So if you're gonna go from doing a PhD thesis or being in academia and being CEO of a company, you're gonna have to deal with all these things if you want a robotics company to be successful. Oh, and there's one other little problem. Often, by the time you get to there, that brilliant idea, it's not adding any value to the customer. We'll get rid of that. All the other stuff was what was important in what you built. So that's really disappointing. Your ideas may not get into the product. But the other thing is the time. So this is a paper I wrote in 1986, an internal memo at MIT. And I talked about building vacuum cleaning robots. And I said it wouldn't be a robot that looks like a person that carries the vacuum cleaner around. Rosie, the robot in Jetsons, was the people's view of a cleaning robot at the time. Said it will look like a vacuum cleaner that's been modified, and it could be insect level intelligence. So that was 1986. How it played out. First prototype in the lab in 1992, 6 years later. By the way, the computation system was from my company, iRobot, and it was hand-built by me and the other two founders, Helen Grainer and Colin Engel, and then we donated it to the lab. That was 1992. 10 years later, we got the first Roomba product out. So now, that little count at the bottom, we're 16 years in to get this first Roomba out in the world. And really, it was successful. I'll talk about that a little about that in a minute. But it wasn't everything. In fact, one of the problems with Roombas for many years was the user had to clean the brushes. And guess what? No users ever cleaned the brushes. So things got gummed up after a while. It was some clever mechanical design. Mechanical engineering is important for robotics. 2013 with self-cleaning brushes. So 27 years after the first publication, that's how long it took to get to really, I think, a successful product. It's a long, long time. By the way, the Roomba would have failed dismally, totally dismally, if it ever fell downstairs. We would have gotten sued up the wazoo. So what did we do about that? Well, this was a major research effort in the company. There's a view of the bottom of the Roomba. This is still, these things are still there today. There's triple redundancy. There's these cliff sensors, which are downward looking infrareds, which detect a cliff. This front caster has to bear the weight of the robot. And if it ever drops, the robot thinks it's on a cliff and stops. That's clever mechanical design. The weight distribution was very tricky for that. And the third thing is wheel drop sensors. So when the side wheel does drop, it may be going off a cliff. Or if you pick the robot up, the wheels drop and it shuts down. So it's double duty there. It was a really fairly cheap solution in terms of the budget we had for cliff detection and not falling downstairs. Totally important, but this thing could never be an academic project. Some of the big problems, you know, intellectually hard problems in robotics, in products, just won't fit as academic projects. They're different sorts of problems often. So that's the first message. Be prepared to be disappointed in time and scope. It's hard work. Now, physical robots in academia need to work for the duration of an experiment. In a startup, the robot you have needs to work for perhaps tens of thousands of hours. The market expectation at Rethink Robotics was that the robots had to run for 35,000 hours with no maintenance and no intervention from a user, if that was the case. They just had to work for 35,000 hours, which is a long time. No reboots, maintenance, etc. The physical robots in the lab are cared for by graduate students, and many of you who are on this, you know, watching this today know that, how much care and feeding it takes to keep your robots working. Whereas in, you know, a product robot, the owner thinks they paid too much, they don't care about how it works, they just want it to do the job. They have no care for the robot. In academia, you can have arbitrarily sucky startup interface full of Linux commands to get things running. In a product, it just has to work out of the box, and there can be zero cognitive load on the end user because they'll reject it as a product otherwise. And in academia, the audience, the people like us today who are watching these great talks and the great 1-minute clips, are fairly forgiving about pretend. You know, suppose this is the case, then this is the technique I'm showing now. Whereas for a real product with end customers, there's zero pretending. It just has to work as it is. You can't say, well, suppose such and such. There is no debate, no argument like that. So what that means is, in a startup, the thing that you build is sort of academically disappointing and sort of dumb. And I went through this with my colleagues, who shall remain nameless at MIT, with Roomba. When Roomba started selling, they would say things like, well, that's not a real robot. A real robot would do X. And I say, does your robot do X? Well, not yet, but we're working on it. We're working on it. And, you know, that argument went on and on. And, you know, 30 million Roombas later, their robots still don't do X. But that's okay. They've done great research in the meantime. But you have to be prepared to deliver. And I tell everyone who joins my companies that you are going to be disappointed with how much we deliver compared to the vision that we have, because it's just got to work out of the box. But these things on the right here that you have to have for a startup imply certain things. It's, you know, they present a high bar. There it is. It says right there. That's a high bar. What is the highness about? Well, it's about environmental complexity. You can't get away with saying this robot will be great at tidying up as long as everything's on the tabletop that you want tidied up and they're all bright colors and easily separable in vision. You have to deal with clutter. You have to deal with real mess, real homes, or wherever, real factories, whatever it is. You have to deal with environmental complexity. You have to get over that high bar. Because below that, it's not going to be a viable product. People aren't going to buy it. Oh, now I have to, you know, clean up for the robot all the time so it can do its job and it's supposed to relieve me of something. No, you have to get that high bar. So there's another axis here though, and that's task complexity. Ideally, you want this gold star here. You want your robot to be doing complex tasks in complex environments. That's what you want. That's your long-term view. But how to get there from the starting point when you start your company? From the robot doesn't do anything and it doesn't really work in any environment. Well, I think, I hope my mouse is visible here. Around this star, if you're moving in this space around here, it's a really high gradient, no matter which direction you approach this gold star from. It's going to be a high gradient. Well, you could try to get there by first demonstrating complex tasks and then ramp up the environmental complexity. But maybe you run out of money before you get to this, or during this really steep ascent. There's another vertical bar here, actually, over what is sort of minimal in terms of the task that could be of value to an end customer. And so another way of thinking about it is to take this path. First, work on getting the environmental complexity before you get over here to this really steep space, so that you get across this vertical here to where it's both a viable product in terms of environmental complexity, and it does enough task for someone to be excited, or enough people to be excited to buy it. You know, then you can keep going here, but hopefully by now you've already got revenue, and you're less likely to run out of money as you get to this gold star. And by the way, you know, as I showed before, that could be in my case, it was a 27-year process to get there. I recommend, if you want your research to be used in industry or used in a startup, rapidly go towards the complex environment in which it's ultimately going to have to run before you get too fancy and show off. Oh, look, it can do this, it can dance, it can use a hula hoop or whatever. I'm joking there. But go for environmental complexity over task complexity first. And that's hard work, but it lets you be in a space where you can generate revenue before you die. So if you want your research to feed into a startup, favor robustness in complex environments over complexity of tasks. That's, I think, my most solid piece of advice for today. By the way, you know, I've been talking about customers and how important they are, and they are important, but man, oh man, customers are pains in the butt. There's irrational, you know, there's tension with customers. So the current irrationality that is being seen by a lot of robotic startups, and it was certainly seen by my previous one, Rethink Robotics. And I'm sure that some of the faculty, I know that some of the faculty who presented earlier today have seen this in their startups, that the customers want a single robot doing a task that was previously done by a human at the same speed or better as a human. Well, you could put 2 robots in there and you get the throughput. Now, there's a cost issue, but it doesn't necessarily, from a rational point of view, have to be as fast as a human. But this is what we keep seeing in customers in manufacturing robots and pick robots. So, well, how did Roomba get away? Because it wasn't a great cleaner. How did it get away with not cleaning as well as a human? Well, fortunately, our early market was people, often grad students, who didn't clean their apartments at all. So we didn't have to compete with someone who cleaned well. We just had to, if we took a bowl of dirt out of the apartment once a week, it was way, way cleaner than not. So we were competing with 0, not competing with a human. And that, partially that was because it was it wasn't a green field if they were dirty apartments, but you get the idea. There is that. But here's the second point: make things work in the most outrageously hard environment first, is my advice. Theorems and formalisms in robotics. Now, I just want to point out, I was trained as a mathematician. I had a classical Eastern European education in mathematics. In fact, I don't know if Rosina is on, but Rosina and I actually shared the same analysis professor. She learned from him in Bratislava, and I learned from him in Adelaide, Australia. So I love theorems, I love formalism. Some of my best friends are theorems. I'm not biased against them, as people say. But they're usually not worth the cost of their assumptions, because formalisms and theorems come with assumptions about the world. And making those assumptions true is often a very expensive thing, and maybe it's too expensive for you to work in a complex environment and have them true. If the assumptions are not true, then the theorems are not worth as much as you thought. So the implicit assumptions of many theorems and formalisms in robotics are that actions in the world are about things rather than coordinates. And by the way, most of the big industrial robot companies are not there yet. They're still talking coordinates for industrial robots rather than things, but everyone here today has been talking about things. Actions can be atomized or atomicized as an assumption that people have. Things in the world are perceived, things that are stable in the world are perceived as stable in the world, but we all sort of know that's not quite true. And there's another assumption, which is less made today, that the world is static except for what the robot does. And this has been known for a long time. This is the Shaky team at SRI in Menlo Park in the late 60s, early 70s, the robot Shaky. And not dissimilar to some things I've seen today, the environment of Shaky was fairly clean with well-colored matte objects rather than being complex environment. This is a screen capture from the Shaky movie. I recommend the Shaky movie if you haven't seen it. If you go to my MIT website, it's ultimately there. But that's Richard Fikes on the left, Bertram Raphael on the right. I'm not sure who it is sitting down, but they're doing the triangle table for strips planning. And I'm sure most of you have seen a strips planner-like thing where these atomic actions, preconditions, postconditions, etc., but atomic actions. And that's how all the publications were about Shaky. But there was another truth below, which turned up in some internal reports, and Nils Nilsson put them together into an external report when he was at Stanford in 1984, that there was some other dirty secrets inside Shaky. At the bottom, the low-level actions were just, sort of motor commands, roll a certain distance, pan the camera a certain direction, etc. But in between those low-level actions and the strips planner, the Macrops and PlanX, were these things called intermediate level actions. And I actually didn't know about these till much later. They just weren't talked about. And these intermediate level actions, and here's the simplest one I've found, it's not one of these actually, because the publications were different at different times, were finite state machines with no guarantee on termination and no guarantee on how long they would take. If you look at this, on the left, there are labels for the states. There's a predicate. When you're in the state, if the predicate is true, you do the actions, none there, and then go to the next state. And these are returns, but here you jump around in a loop between 4 and 2 and 3, doing various sensing, calling other intermediate level actions. And this was there. And I sort of look at this as the purpose of these was to mush time and actions into looking atomic to the high level planner. And we still do that. All our systems do that. And by the way, there's Charlie Rosen, who's head of the project, dressed as a gremlin in the movie. He comes and invisibly moves something around. And even though there was a static world assumption, these ILAs enabled it to be robust to some non-static things. So that was what happened in Shaky, and it happens in all real robot systems. There are these things that mush stuff into the higher level assumptions. But we also have that in perception. Deep learning labeling has confused us to think we have symbol grounding solved, but in a sense we don't really yet. There's also problems of stability of the grounding, which involves ongoing perceptual smoothing and integration, and all real systems have that somewhere. Brian Cantwell Smith has written a really good book about this. For those of you who've read any of his previous writings, like his 800-page PhD thesis or his mid-90s book on objects, this is not as bad. It's only 150 pages, but I still, as a native English speaker, had to go to the dictionary all the time to figure out a lot of his words that he uses. But it's a deep book and it's interesting. And he calls this process, or this thing, the process of registration. It's richer than grounding that we actually have to do to make things work in our robots. So all execution systems have something like intermediate level actions or intermediate level perceptions. I just made that up. And they're a mechanism to maintain the assumption of the theorems. but they're not. The assumptions are not necessarily met. These ILAs and ILPs sort of let you pretend about the world that it's stable, and they're not really. So often, certainly optimality theorems, which are often fairly unstable on their based on their assumptions, don't work out so well and not so useful. And so for all the robots I've built and delivered to homes, factories, planetary roving military, and even the robots that shut down Fukushima, they all intrinsically assume that everything is unstable and try and compensate for stability at all times. And having an optimal algorithm is usually not good enough. To get something that's good enough, then it's optimal. And so this is sort of a recast, playing on words here, a recast of Herb Simon's satisficing description. Herb was one of the founders of AI, one of the 4 principal founders of AI, also won the Nobel Prize in economics, that satisficing, good enough is what you need, and how you get good enough. And enlightenment in the world of deployed robots, and I'm not criticizing academia here, I'm saying for deployed robots, your enlightenment comes from empiricism, measuring, testing for thousands and thousands of hours, rather than from proofs, which I liken to faith because the assumptions are so unstable. So that's my third message I wanted to say today. And as I was writing the slide, I realized that, the second message here, I was saying, don't pretend, no pretension. And the third one is no pretension in industry. With that, I want to finish, but I do want to say that Robust AI is hiring. We've doubled in size since COVID hit. We're a distributed company, and we want to double in size again now. So send email to Rodney at robust.ai. I'm not sure you can see it right there on the right. That's Rodney at robust.ai. If you're interested in, if these messages I gave today didn't scare you off too much and you want to work in industry, we would love to talk to you, and be safe in the meantime. And with that, I think I'll switch to questions, and I don't quite know where I'm going to get questions from.
All right, thank you so much for such an inspiring talk. That was awesome. All right, so let me just look at questions over.
By the way, in industry, people aren't as polite as you are. Thank you.
Try to be polite. Okay, so actually, let me ask a question first, and then I'll get back to the YouTube one. So like you talk about good enough, like who defines good enough? Like, for example, when you think about autonomous cars, right? Like, when is it good enough? Who defines, like, when is this good enough, like in general, when you're thinking about these problems?
Well, in the case of autonomous cars, and I've been writing about this for years, the assumption that there was going to be a one-for-one replacement in our existing road network with human drivers on the road at the same time says that good enough has to be human level performance. And we're not going to get there soon. We're only going to get to autonomy by working in restricted environments. And we see more and more people talking about working in enclosed, geographically localized places where all the other drivers are trained, a campus-like environment where the public can't drive on there. So that as a startup company, you have to look at where you're going to sell, whether it's software or physical robots, and what the environment is going to demand, and then and talk to customers early on, and from that get an empirically testable notion of what's good enough. Autonomous driving did not do that. That was not the way it was. And there was a story in the information last week that Uber regrets wasting $2.5 billion on it. I could have got a not working system running for much less than $2.5 billion. I would have been happy to waste less money. It would have been cheaper. But, yeah.
All right, cool. So we have a couple of questions. Let me actually, Erdem has a question. Do you want to, Erdem, ask your question?
Sure, yeah. I was asking, do you think if it makes sense to try to bring academia closer to industry, or is it better to have all these differences between the two?
I think the difference is healthy in many ways, because companies can't be as innovative as academia can, but one has to understand, and it only works in countries where there's funding agencies which are tolerant of failure. Most things are going to fail. Most things are not going to be used in the real world. Most things may trigger some thought years later, but they're not going to be used. So you have to be tolerant of a very high failure rate. You know, in the US, we have the venture capital system, stronger here than many other countries, and they pride themselves on being tolerant of high failure rates, but they're nothing like the failure rates in academia. And so when I was last at MIT, I was always trying to figure out how to raise funds to do truly outrageously weird academic stuff, but I could never get my academics to agree to it, and they would never let a graduate student do truly outrageous stuff. The only place that seemed possible to get truly outrageous ideas looked at was with undergraduates. And then when undergraduates realized they needed papers to get into one of the best schools, that went away too. So we're, you know, the scale of academia is sort of killing the risk, what I think is the high risk stuff, which is probably the best thing that academia could do. Be riskier. Graduate students out there, ignore your professors, do risky stuff. No.
Thank you.
All right, so we have a question from Ken. So Ken is asking, before I order Cantwell Smith book, can you say more about how registration differs from grounding?
Yeah, it's about the, he uses a bunch of examples, but it's about, and I recommend Smith's book just to improve your vocabulary. You know, that alone is worth it. But his registration is about what the ongoing relationship between the observer and the object is, and how it may change through different perceptual systems at different times, and what is the essence of the objectness that is there. His point has always been, in his 1995 monstrous book, which is, I don't recommend, it's really hard to read, was that, you know, we tend to think of objects as just being there, but objects are one of the great inventions of human minds, and they have to be likewise maintained and invented in our AI systems. By the way, I was surprised in this new book, 2019, about Brian's generosity towards deep learning. I wasn't expecting that. So don't be scared, you know, that he's going to say deep learning is bad, don't do it. He doesn't say that at all.
All right, I have a question.
Goldberg?
Sorry, what?
Who was that? Was that Ken Goldberg?
That was Ken Goldberg, yes, yeah.
Yeah, Ken, you can read big books, it's okay.
Cool. I have a question from Claire Tomlin. So Claire is asking, what do you think should be the fate of theorems in robotics?
Well, here's the problem. Theorems and optimality, you get to, you know, too often you get to choose, you know, what it is you want to optimize, and then you get to choose the norm that you use, and it's often driven by getting a theorem rather than by having something really work in the world, which is why not so useful in industry. You know, I know that I know better than to say academics shouldn't prove theorems, so I'm not going to say that.
All right, so I have a question from, I think, one of the students. So Adi is asking, so as Roomba is joining dishwasher and laundry machines as one of the most successful robots in homes, what is next? And also, she's also asking, like, what took 27 years? Is it building consumer product, or which part of it that was actually taking 27 years?
Well, it was a whole bunch of things. Some was, I'll answer the 27-year question first, and then the what's next. It was a bunch of things. Like, we had that product on the market from 2002 until we figured out how to make the brushes self-cleaning. It just took it was clever mechanical design, and it just took a lot of work, a lot of internal research to get there. When I first talked about the idea, we didn't have the technology to build a prototype even. That was 6 years later when we could finally get enough stuff off the shelf to build the vacuum cleaner. By the way, the bad thing about that vacuum cleaner was it was designed by computer scientists. It sucked the dirty air through the computer boards, which was not a good idea, but it was enough for a pretend and a demo. But to get from that to a product which retailed at $200 was another big project. We were not the first robot vacuum cleaner on the market. The Electrolux had the Trilobite, which, by the way, Henrik Christiansen had worked on, and it sold for 2,000 euros. We didn't think many people were going to buy a 2,000 euro vacuum cleaner in 2002. We went around to shopping malls and we asked people by themselves, how much can you blow on a impulse purchase for a gadget without your spouse divorcing you? And the answer came out around $200. And so that became the first thing that we had in a big spreadsheet. The bottom right-hand corner was $200, backed up all through, all the costs, et cetera, for the bill of materials, and then designed that bill of materials. And that was a long, hard process also. That's why it took so long. Getting the price point and getting the usability of it. What's next? I don't know exactly what's next, but I know that there is going to be a tremendous pull because of the demographic inversion of letting people stay in their homes longer as they get older with dignity and independence. And anything that can help that will be important. What those if they're, we've got lots of products which are not robotic, which help the elderly remain in their homes longer. If there is something in robotics that can help, maybe one of the biggest reasons people have to leave their home and go into managed care is when they can no longer get into and out of bed by themselves. Maybe it's a robot that helps people get into and out of bed. I don't know.
Okay, thank you so much. So I think we are out of time. So with that, let's normally, if it was an audience, like we had an audience, I would ask. Let's thank Rodney. We have more than 200 people watching, so I think they're thanking Rodney virtually. And I think we can basically, take a break now for 15 minutes. And let's try to be back at 12:15 for the last set of faculty talks. This is the last part of our program today. Thank you again, Rodney.
Okay, we are.
Okay. Welcome back, everyone. This is the last session of BARS. We've got a fantastic lineup of 6 speakers to go. So I'm going to start directly with Mykel Kochenderfer from Stanford.
Great. I think you can see my screen now.
Looks good.
Great. I'll talk about a small project that we've been working on in the lab. This is summarizing some work by my PhD student, Kyle Julian. We started this work a few years ago on neural network verification. The idea was that we have a neural network representing a collision avoidance system. And what we want to do is prove properties about the policy. So here's a slice through the state space. When we look at this plot, it looks like everything in the top red square is a descend 1500 feet per minute advisory. But of course, that doesn't mean to say that if we zoom in here and look between those pixels that there might be some other advisory like clear of conflict or do not climb. So this was in collaboration with Clark Barrett in the computer science department, and we developed the ReLUplex algorithm for proving properties about these neural networks. And of course, a number of other labs produced a number of other algorithms for verifying these properties. And one of my postdocs produced a survey and a re-implementation of all of these algorithms in Julia. So what we've been working on lately is using this to prove or find failures in neural network controllers. This application was trying to find errors in a controller for a system that steers an aircraft along a taxiway or runway. This is how it works. It takes as input an image, then it downsamples the image, turns it into grayscale. Those pixels are input into a neural network. The output is a cross-track error and heading error. We use a simple linear controller to steer the aircraft to the left or to the right. And then this gets updated once per second. So we trained the neural network, and we found that it actually works pretty well under different lighting conditions, different times of day, and it very reliably stays on the runway center line. And what we did was we combined this with these neural network verifiers to try to find perturbations to the image that would get it to steer off the side of the runway. So here you can see the trajectory of the aircraft along the runway. You see the true image, the downsampled image, and the perturbed image. We allow perturbations of about 3% for the pixels. But what we found was that we couldn't get it to steer off the end of the runway. When we got to the left, there was no amount of allowed perturbation that would allow it to continue off the side of the runway. So what we did was we combined this with a technique that we've been developing called adaptive stress testing, which tries to find the most likely failure scenario given a black box system and a model of the environment. And what we got are very interesting failure scenarios. If we're limiting the perturbation to 2%, we couldn't get it off the side of the runway. But if we bumped it up to 3%, we were able to find some very interesting failures. So on the top right, you can see how through these perturbations, we can get it to steer off to the left side of the runway. But then it figures out that you can perturb the image to make the aircraft go off to the right. And it finds itself in a situation that's very different from the data that it was trained on, and it actually blasts through the right side of the runway. If we bump that up to 3.5% or 4%, we get other kinds of failures. The likelihood of the perturbations is related to how much we allow the pixels to be perturbed. And it found, so on the bottom here, it found that if it does these perturbations and gets it to steer in between the dash marks of the runway, we can get even more likely scenarios, because failures because it doesn't have to perturb the image as much. And I think I'm pretty much right at time. I do want to mention that I have most of a draft ready of our new algorithms for decision-making book. You can find it here. This is joint with Tim Wheeler and Kyle Wright.
Excellent. Thank you, Mykel. Let's go to some questions. So I'm not seeing any questions in the chat yet. Maybe I have a question. Sort of, if I think of flight versus this sort of runway operation, are there fundamental differences in these operations as far as these algorithms go?
Are there different? Sorry, I missed that.
If I'm flying in 3D space, I guess, versus driving on the 2D runway, are these fundamentally very different operations?
So, I mean, there's still physical state spaces. I mean, spatially, they're three-dimensional or two-dimensional, but in reality, there are a whole bunch of other state dimensions that we have to keep track of, like velocities and accelerations and so forth.
Excellent. Well, thank you very much, Mykel. Really cool stuff as always. All right, thanks a lot. Up next, we have Silvio.
Hello. Thank you, Mark.
Go ahead and share.
Yes, let me show the screen 1 second. Share. Okay.
Silvio Savarese, and
okay.
At the moment, I can see your desktop only.
Right. Can you see now?
There we go.
Okay, great. Okay, so
we dream the day when robots may roam our homes, putting away our dishes.
One sec. Sorry, I have glitches in my system. 1 sec. Can you give me 1 minute? I'll need to.
Folding the laundry, sweeping the kitchen.
1 sec. Are you guys still? Do you see my screen or?
I see only you at the moment. Your screen disappeared.
Okay, so give me just 1 minute. So 1 second, I need to stop something here. Okay, so let's see if I can do this. Okay. Does it work?
I'm only seeing your desktop.
Okay.
Oh, there we go. Now I see the slides.
Okay, great. So, okay, we dream the day when robots may roam our homes, putting away our dishes, folding the laundry, sweeping the kitchen floor, setting up tables, or assisting our aging relatives. But training robots to safely and effectively operate in a home environment is very challenging. Humans have successfully learned how to solve this task throughout their lifelong experience by continuously interacting with environments, by observing how the environments react to certain actions. So what if we can make available a suitable environment for robots to explore, navigate, and perform tasks? In essence, a playground for learning, improving robot skills. So we decided to embark into a daunting task of creating such a playground. After months and months of hard work by multiple students and researchers from our lab at Stanford, we're proud to present a new simulation environment, which we called iGibson. So iGibson provides fast visual rendering of physics simulations in hundreds of real-world environments, like this shown here. It allows researchers to train and evaluate robotics agents that use optical sensors to solve indoors navigations and manipulation tasks, such as opening doors, picking and placing objects, or searching in cabinets. Compared to other existing environments, such as Habitat, AI Tutor, Sapiens, and 3D World, iGibson includes a novel set of unique features. First, iGibson is equipped with a repository of hundreds of large-scale realistic scenes populated with objects. Our scenes are acquired directly from real-world indoors environments, using scanners transformed first into 3D reconstructions and then into 3D large interactive scenes. Because we start from real-world scans, the layout and distributions of objects in our scenes approximates those in real-world environments. Furthermore, objects are annotated with materials as well as surface properties like albedo, shading, and so on. Second important feature is that all the IG scenes are fully interactive. Agents can interact with most of the objects on the scenes by applying forces or engage with articulations or mechanisms. For instance, agents can move cups, books, utensils. They can open doors, drawers, and other elements. This is different to other environments where scenes are either static or actions are regulated by predefined commands. A third feature is that we extend the intraclass variability of each scenes by enabling several types of domain randomizations. For instance, we can randomize texture material, physical properties like frictions, 3D object shapes, while preserving original layout and distributions of the objects. This gives a potential endless variations of configurations for each scenes. A final feature is that we have equipped Gibson with a super friendly web interface. This interface allows human users to navigate and interact with all elements in the scene with intuitive mouse and keyboard commands, and therefore provide large variety of demonstrations. Okay, this is all great, but is training agents in Gibson really helpful? Well, we have carried out a number of experiments that demonstrate that Gibson's new features do actually facilitate the development of interactive AI. And in interest of time, we will focus on just one of these. Specifically, we want to explore whether the ability to interact with scenes elements, such as a cabinet, a door, or a mug, allows to learn mid-level representations that help accelerate policy learning in manipulation tasks. Let me explain this in a few details. As this video shows, mid-level visual representations are visualized with warm colors and corresponds to object regions where agents have learned to be interactive. To discover this mid-level representation, we set up a pre-training phase whereby a virtual agent interacts with random points in the scenes and learns to predict the outcome of those interactions. We then use these pre-training mid-level visual representations to train agents in manipulation tasks. We were excited to observe that agents using these mid-level representations do train quite faster and with a high performance. As this plot shows, blue and red curves correspond to training accuracy as function of training time. Red plot shows training accuracy without pre-training with the mid-level representations, whereas red curves shows training accuracy as mid-level representations are used. Left and right panels correspond to two different examples tasks, open cabinets and pull drawers. As you can see, in both cases, the blue curves ramp up faster than red ones, which indicates pre-training mid-level representations does speed up training.
So it's the time warning.
Gibson has been a key development tool in many projects in our lab and outside Stanford. This includes projects on interactive navigations, mobile manipulations, and mechanical search. The latter is a collaboration with Ken Goldberg at Berkeley. As final note, I'd like to thank all the amazing team behind Gibson, and in particular, Roberto toward the latest release. And I would like to also thank our external collaborators at Stanford, Google, NEC, and Toyota. And with that, I would like to thank you for your attention.
Excellent. Thank you, Silvio. I'm going to give a moment for questions to appear on YouTube, because I think I'm always in too much of a hurry. So maybe while we wait for the question, Sergey, if you want to go ahead and just share your screen. Okay, I think I've been polite long enough. Let me ask my question. In terms of the simulation, do you guys also, does the simulator come with its own physics for the robot, or is this something that I could easily plug in? Let's have a weird robot that I want to test in your environment. Is that easy for me to encode physics into your simulation?
Sorry, I missed your question because the line got broken for 1 second. Can you say it again?
Sorry, the simulation for the physics. Can I plug in my own physics into your simulator in a straightforward manner? Let's say I have a bizarre robot that I want to simulate.
Right. So you could plug new agents into the environment, but so currently there are a number of agents already installed and that can work out in the simulator. But if you need to add a new one, you could import it, but you need to do some work to interface it. But the infrastructure should be quite flexible that you could easily add more agents.
Excellent. All right. Thanks a lot, Silvio.
Thank you.
Up next, Sergey Levine from UC Berkeley. Sergey, I'll let you take the floor.
All right. Yeah, so today I'm going to talk about deep reinforcement learning robotics and data-driven decision-making. And to start off with, I'll start with a big question and a simplistic answer. What makes modern machine learning work? At a very, very high level, we could say that a big part of what makes modern machine learning work is the combination of large data sets and large high-capacity models. We've seen this enable effective image recognition, machine translation, speech recognition, and so forth. So what about reinforcement learning algorithms? Well, reinforcement learning is fundamentally an active learning paradigm. You have an agent that interacts with the environment, collects some data, uses that to improve its model, collects some more data, and then repeats. And it does this many, many times. And we've also seen quite a few successes come from the domain of reinforcement learning for things like playing games and even basic robotic tasks in laboratory settings. But if you want to scale up robotic reinforcement learning to achieve the kind of open world generalization that we've seen from supervised methods, there's a really big gulf. And that gulf is really caused by issues with data. If you have an active learning process and you need data at the scale of something like, ImageNet or MS COCO, but you're collecting data on the fly, you're essentially imagining collecting data of that comparable diversity every time you update your policy. And it's very difficult to make that scale. So can we develop data-driven reinforcement learning methods? Methods that don't require on-policy data collection, or even off-policy methods that log previous data but still collect data online, but rather fully offline, fully data-driven methods that can take a large data set that was collected before and then leverage that data set to acquire a policy that generalizes in a really effective way to open world settings. Of course, in reality, we wouldn't do purely offline training. We could perhaps imagine a robotic learning recipe where you've collected a lot of data from all of your past interactions, use it to get the best policy you can offline, but then occasionally get a little more data to improve it in the places where it's weakest. So I'm going to talk about some offline reinforcement learning algorithms and also ways that we can use them in a robotics context. So first, why is offline RL difficult? Why is it a different thing? Why can't we use existing methods? Well, the problem really comes down to distributional shift, which results in a kind of over-optimism bias. Here's a simple experiment using a standard, regular online reinforcement learning algorithm, but in offline mode. So there's an off-policy method called SAC. It does very poorly, regardless of how much data you give it, but its Q function thinks it's doing extremely well. The y-axis here is a log scale. So where does that over-optimism come from? Well, at the core of any actor-critic algorithm, if it's off policy, is going to be some kind of update to a value function. And the target values for the value function need to be calculated in expectation under your new policy. That's what makes it an off-policy algorithm. But the policy is selected to maximize that quantity. And you can think of this almost like finding an adversarial example, an adversarial action that will fool your Q function into thinking that it's good. So you could imagine that if this green curve is the true function, the blue curve is your fit. The blue curve looks really good, but if you maximize it, you'll find that one point where it's very erroneous in the positive direction. And that's what we see. So we came up with an algorithm that mitigates this issue that we call conservative Q learning. The idea in conservative Q learning is to combine a standard reinforcement learning objective, a standard Q learning Bellman error objective, with a conservatism term that explicitly pushes down on the large Q value. So it finds the actions that are large and directly minimizes them. And that finds these errors and basically pushes them down. In fact, we can theoretically prove that this algorithm learns a Q function that is a lower bound on the true Q function, which means that it's guaranteed not to overestimate if you select the regularizing parameter appropriately. So we've evaluated this kind of setting where you have a data set of past interaction and you want to learn offline. So the setup here, just to explain briefly, is that the robot is going to learn a new task. In this case, it's to grasp this ball from an open drawer. But at test time, something will change. Maybe the drawer now is closed. Now, of course, if you only learn to pick up balls from open drawers, you won't know what to do when the drawer is closed. You lack that common sense. So what we're going to try to do is use offline RL to extract that common sense from prior data. So perhaps you've seen prior data where you've done other things. You've moved objects around, closed drawers, open drawers, pushed things about, but you've never done the whole thing. You've never actually opened the drawer and taken out the ball together. So you have just data for the new task, picking up the ball from an open drawer, and lots of data from other related past tasks, and you need to stitch them together to figure out this new behavior that you've never seen before without ever having attempted it. So the problem setup is that you have your training data, it has sparse 0-1 rewards, you have to learn from images, and the prior data has no rewards at all and just tangentially related skills. And the algorithms just use conservative Q learning. And the basic idea works. So if you combine these parts together, you can get a robot that grasps the ball from an open drawer, but also figures out to open the drawer if it's closed, move an object out of the way if something's in the way, and so on. So you get some pretty sophisticated behaviors out of this. and it even works on a real robotic system, a low-cost robot. All right, thank you very much, and I'd be happy to take a quick question.
Excellent. Thank you very much, Sergey, and very timely. Let's see if there's any questions in the chat. The question, are there any from the other speakers? I feel like I'm totally monopolizing the questions here that would like to ask a question. And maybe, Sergey, you mentioned, the appropriate selection of this regularization constant. Is this something that's hard to do? Is it sensitive to that?
Well, so the theoretical result holds if the constant is chosen according to some equation, but that equation depends on a bunch of, on a bunch of terms that basically come from concentration inequalities, which you typically don't know in reality. So there's an automated rule that we actually have in the paper for tweaking this thing adaptively. So it's somewhat sensitive to it. The adaptive rule seems to work, but that's an empirical result, not a theoretical one.
Okay, excellent. I see there's a question here. It's from Suraj. Let's make sure I parse this. So the question is, you mentioned that you label all task agnostic data with rewards of 0. The question is, does this labeling of potentially good steps with 0 reward cause issues?
Yeah, that's a really good question. We actually evaluate this in the paper. We look at what happens if you have kind of a polluted data set. It really doesn't cause issues, and the reason is a little subtle. The reason is that you still get the Q function from the backup, and even if there are some good things in the prior data, they are so few in proportion that little bit of pollution doesn't really hurt you. So it's kind of safe to assume if you're learning some new task, everything you've seen before doesn't succeed at that task, but it could still be useful because of the target Q values.
Okay, excellent. Thanks, Sergey. Maybe you can release the screen. Mac, you can share.
Okay, great.
All right, up next we have Max Schwager from Stanford.
Is everything showing up all right?
Looks good to me and I can hear you fine.
Great, thank you. Great, okay, so I'm Max Schwager. I'm assistant professor of aeronautics and astronautics at Stanford. I'm generally interested in multi-robot systems. So I'm interested in developing algorithms that enable groups of robots to efficiently coordinate and collaborate together on common tasks. So I'm going to talk today about a recent project on drones counting penguins. So this is my PhD student, Kunal Shah. He looks a little bit worried. Why does he look worried? Well, if you zoom in on his parka, you can see that he's actually a member of the US Antarctic program. And in fact, he's worried because he's just about to ship off to a remote field site in Antarctica. It's actually on the side of the Ross Sea. It's a site called Cape Crozier. And if you zoom in a little farther, you see Cape Crozier is covered in a bunch of little dots. Those dots are actually these adorable little Adelie penguins. Hundreds and hundreds of thousands of adorable little Adelie penguins. So the reason why Kunal is worried is because this all happened about a year ago. He was, had multiple trunks in hand and was about to board a military transport aircraft to spend 3 months on a remote, icy Antarctic field site taking aerial surveys of penguin colonies. So let me tell you a little bit more about this trip. This is all work that was recently published in Science Robotics in the late October issue. So all the imagery that you're seeing here in this video was collected by Kunal and our collaborators during this trip to Antarctica. So the challenge here in deploying drones to do aerial surveys of large-scale colonies like this is speed. So you saw in that previous image, the weather can be terrible. The site is very remote. It's only accessible by helicopter. The penguins are very broadly dispersed over multiple square kilometers, and the terrain is very severe. So these drones actually have to fly over fairly large and rocky mountain ranges in order to get to the colony to be able to take the survey. And here you see the image from on board the drone to take the survey. So all of this needs to happen very quickly because the drones move, the weather changes very quickly, and if you have an opportunity to take the survey, you just want to take the survey as quickly as possible. So existing methods for these kinds of surveys would use a single drone with a raster style pattern, which is actually very inefficient. Instead, our method uses multiple drones acting together So they can cut the survey time in proportion to the number of drones we're using. And the trajectories that our planner produces are very interesting and convoluted, and the drone's trajectories actually interleave with one another. So this illustrates the trajectories that our solver finds. I'll tell you a little bit more about the technical details in our solver in a second. But our solver finds these drone trajectories, then we upload these to the flight software and launch the drones, and then the drones go autonomously and collect the images for the survey. Thousands and thousands of images. So the scale here is really important. We're talking about 600+ thousand Adelie penguins at the beginning of the mating season, and then close to 1 million afterwards, after they've produced their young penguins. All of this work was done over the course of a 3-month stay, where the researchers, Koushil included, were just camping in tents on the ice, as you can see there, and under really severe conditions. So we're excited to be able to demonstrate that our autonomous robotic system can be deployed in these kinds of conditions. So let me talk a little bit more about the algorithm. So as I said before, standard planning algorithms for aerial surveys use a sweep style planning geometry. So you can see this in the upper left, the paths just sweep back and forth, and there's no inherent facility for multiple drones to plan their paths to interleave with one another to cover the same area. So our algorithm, which is called Popcorn, that's an acronym. I don't remember exactly what it stands for, but so the way this works is that, in fact, we use multiple instances of an SMT solver, satisfiability modulo theory solver, to find feasible paths that meet several logical criteria for the survey, and then we sort of step down an upper bound on the length of these paths to ultimately reach length optimal paths for the drones. And the solver naturally accommodates an arbitrary number of drones. Again, the goal here is to collect the survey data as quickly as possible. And furthermore, the paths that we obtain are much more path efficient than the sweep planning algorithm. So we're not only interested in surveying large-scale penguin colonies, we're interested generally in any kind of large-scale environmental survey that would be of interest, where, you know, autonomous drones would be helpful. So we've already deployed our system over Mono Lake to do surveys of actually an island chain to study the bird colonies that nest on this island chain. We've also deployed over a very large cattle ranch in Napa Valley, just north of San Francisco, where the ranchers were interested in learning more about the density of their vegetation and the diversity of their vegetation, so they can understand the how large the cattle herd was that they could support on that existing vegetation. We're also interested in deploying this over forests to monitor for forest fire risk, deploying over disaster sites to collect information, and so on. So I'd like to say thanks to Koushil, who is the real brains behind this work, and to our collaborators who are ecology scientists, Annie and Grant. And thanks to all of you for your attention. I'm happy to take any questions.
Excellent. Thank you, Mac. That's really, it's a really extreme project. I like it a lot.
Thank you.
Give a second here for questions to pop up. Maybe a quick question from my side. I imagine there's many practical constraints when you're operating in Antarctica. Was it hard to operate your robots there harder than you would have imagined, or were you reasonably well prepared?
So it was very hard, but I'd say some of the biggest challenges came from the administrative requirements for flying autonomous vehicles. So basically, the NSF is in charge of those requirements, and they have enacted the similar requirements as the FAA within the US. So those requirements are that there must be a human pilot ready to take over control of any drone, and there must be a human pilot who has a visual line of sight to any drone at any time. So that means even though we had lots of drones flying autonomously, we required lots of drone pilots sitting around observing everything to take over in case something went wrong. And those pilots had to perch themselves on the side of steep mountain slopes and within the penguin colony with penguins buzzing around them. Even though they didn't do anything, they had to be there. That was challenging.
Interesting. There's a great question here from Shreyas. Maybe, Mac, I'll ask that you turn off your screen sharing.
Sure.
And let Alex take over on that front. Shreyas asks if you have, especially for younger professors or postdocs, if you have advice how to find such collaborations, for example, with ranchers or counting penguins, etc.? How does one build that network?
Oh yeah, so I think serendipity is the answer. I wish I had like a surefire strategy for you, but I don't. So in fact, I made my connection to these researchers at a wedding, at a family wedding. So Annie Schmidt, who is one of the co-authors, is a good friend of my wife's sister. And we were sitting around talking at my wife's sister's wedding, and she said, I study penguins in Antarctica. And I said, I study drones, and I like to deploy my drones in extreme environments. And she said, great, let's write a proposal. And that's how it happened. So I think just be open to serendipitous meetings. And of course, you can always reach out to scientific collaborators also. And I think people generally in the sciences are interested to collaborate.
Excellent. Well, thanks a lot, Mac. I noticed there's a bunch of questions that popped up, and maybe ask that you take them on YouTube. And then we'll give up next Alex Bayen from UC Berkeley. Alex, I can see your screen well.
Okay, wonderful. And can you hear me okay?
Hear you fine.
Fantastic, thank you. Well, thank you both the organizers for inviting me. I'm very excited to present today. I'm going to talk about energy optimization of mixed autonomy traffic at scale. This is joint work with a consortium of 5 universities, Berkeley, Camden, Rutgers, Camden, Temple, University of Arizona, and Vanderbilt, as well as the Tennessee Department of Transportation and a few car companies, and of course, Bayer. You can see the name of all the collaborators here. So I think the motivation for this work is something I showed at BARS last year. You probably remember that seminal and pioneering experiment of Dan work a few years back, where the self-driving vehicle outlined here by the arrow at some point is able to smooth these oscillations of traffic that occur naturally. You can see now the autopilot being turned on and the smoothing happening. This was foundational because, to our knowledge, this is one of the first, if not the first, experiment in which mixed autonomy traffic was demonstrated, and in a way that was quite spectacular. The fuel savings for that experiment were 42%, which is gigantic. Now, of course, this is a contained environment, it's a parking lot, but this was really the beginning of a quest. And today, 1 year after last year's Bears, I want to show you a little bit more where we are on that quest. So, since then, there were a bunch of tests that were run, in particular on string stability. So now kind of bringing these findings to the real world. So these tests was also run by DanWorks group. And here the idea was to show that even if you have adaptive cruise control turned on for all of the vehicles, you can still produce string stability, string instability, leading to very bad performance and fuel efficiency. And so the notion and the quest we embarked on since then was to say, well, if you had control over, say, 5% of the vehicles, say your typical Tesla level 2-ish automation, could you smooth traffic? And so the target, number one, I guess, for these studies is essentially stop and go waves. Stop and go waves, you can see this in a little window here, are waves that appear for no reason on freeways, just due to the fact that humans are not very good at regulating, and which are responsible for an enormous amount of energy waste in traffic. Our hope is that with, say, maybe 5% of vehicles working together or independently, this could be smoothed out. And our findings in this first year of this project we are now doing for the DOE is that with 5% of the vehicles, we should be able to shave 10% of fuel inefficiency, which is huge. So the type of scenarios we're looking at now are located around the I-210 in Pasadena. This is a model we inherited from another project, the Connected Corridors project, which is essentially a model that took 3 years to calibrate for the California Department of Transportation for control of traffic purposes, but which we're also using for this mixed autonomy work. And the way we think about this is that you have these level 2 automated vehicles, longitudinal mostly. They can sense some of the vehicles, which are indicated in blue. So red is automated, blue is visible to the automated, and white is invisible. There's no information whatsoever transmitted to the red. So the notion being now, can we try this? And can we create a set of scenarios in simulation and anticipation to an actual deployment to demonstrate what we've done in simpler scenarios? So for that, there is already a lot of work needed to even construct the waves. It's actually not that easy to reproduce these waves in simulation. And of course, if you're going to train deep reinforcement learning algorithms on it, you need to have a training scenario, which needs to run in simulation. And so a lot of the work, that part of the work was done at Vanderbilt, and essentially managed to recreate these waves at the proper frequencies so the algorithms could learn on them. These waves are shown here. You can see this is called a space-time diagram. So you have time and location on the freeway, and you can see these waves propagating, which are responsible for these energy and efficiency. And so this, in a sense, is the training set that we use for these algorithms, where now what the RL controllers do is essentially learn from that in different settings with different penetrations until policies can be deployed in the simulation. So that, once it's finished, enables all kinds of settings. You could do completely decentralized, you can do hierarchical, there's lots of different things. For that, we need a reward function. And so for now, this is fitted for Tacoma model, but we're already working with Argonne National Labs, and with autonomy, we're going to have a couple of access to over 200 different models, or 150 models, sorry. And from that, select maybe the 10 most representative that will be used for real setting, because at the end, we want to be able to learn based on energy functions. And so what the typical way these algorithms work is, you can see what they do is they shave these waves. So you can see on the left kind of a baseline scenario, and then you can see a multi-agent RL scenario here, where now these waves have disappeared.
Time warning.
1 minute warning, thank you. And so this is typically what we're looking at.
30 seconds warning.
30 seconds warning, but this time is going faster than real time. And then of course, the type of work we do is we look at the penetration rate. And so trying to look at, even at small penetration rate, you'll get a 20% improvement in the energy, which is really good. And then we do a lot of robustness testing, but I'm not going to have time to do it. I'm going to show one last thing when we use hierarchical RL. And here the idea is, again, we have much more aggressive ways to shave these waves, again in the spirit of energy efficiency. So I think I've exhausted my time, and I'm going to stop here.
Thank you very much, Alex. That's really cool stuff. Give a second for a question to appear on the chat.
Yes, did we consider, yes, I can see the question, did we consider other vehicle communication models that do not require leader information? Yeah, so this is a fundamental question, because in doing this, you have to make all possible of assumptions of architecture, anything from everybody talks to everybody with infinite bandwidth and no latency, to essentially, at best, you might get some traffic information fed to you, maybe, and then you have to do a local control. So we're exploring all paradigms in between these two extremes I just showed. And some of the results work decentralized. So in other words, you don't need to be fed leader information. The reason why you're asking the question is obviously because in string stability is very important. So we're working in ways that we don't have to have that information fed, because we believe ultimately that's the goal. Obviously, it's much harder, because once you lose the centralization and that information, the algorithm's performance degrade further.
Excellent. Thanks a lot, Alex.
Finally, I'm wearing Stanford color today. Just want to mention this.
I will not comment on that. Up next, our last speaker, Marco Pavone. Marco is also one of the previous organizers for BARS. That's it. There we can see your screen well, Marco.
Great, thank you, Mark. First of all, I would like to thank Mark and Dorsa for organizing BARS this year in this new virtual setting. I think you have done an amazing job, and I really thank you for that. So let's start by saying that a key focus of my lab research is on interaction-aware decision-making, where we seek to devise controlled policies that allow a robot to interact with human agents in a safe and efficient way. Our approach is model-based, whereby a probabilistic understanding of the interaction dynamics is used as the basis for policy construction. Now, within a model-based approach, a key step is to design models for intent prediction and trajectory forecasting. Our main result is a Trajectron++, which is a generative trajectory forecasting model that uses conditional variation autoencoders at its core. Trajectron++ reasons about agents dynamics and yields state-of-the-art performance on a variety of different data sets. In particular, and in my opinion, this is one of the most important aspects of this model, is that this model can ingest as conditioning variables a vast amount of heterogeneous data. For example, maps encoding information such as road geometries and crosswalks, and even human silhouettes. All of our code, trained models, and data are available at our GitHub page. Trajectron++, however, is quite difficult to use within decision-making. Specifically, Trajectron++, as most of the other methods in trajectory forecasting, predicts individual trajectories, which are referred to as tracklets, basically a sequence of waypoints. And this is a rather natural output structure for trajectory forecasting. However, it's quite difficult to use for downstream control. In other words, this representation is not the most efficient way to inform downstream robotic tasks, as it often leads to computational demanding scenario-based optimization scheme, whereby one has to sample several possible human responses with respect to a candidate robot action. So a key question is, can we devise more efficient representations that are more conducive to planning and control? To address this question, we have recently proposed to represent intent prediction according to a system theoretic formalism. Specifically, the scene is modeled through a linear time-varying system, where the state is a concatenated state of the agents in the scene, and the control, U subscript of R, is the robot control. For example, considering the example on the bottom left, we have three agents. We have the robot in gray that we're controlling, a vehicle, human-operated vehicle, and a pedestrian. In this case, the state will be the concatenation of the states of these three agents. What we want to learn are the blocks in the linear time varying dynamics that represent agent-agent interactions or uncertainty. For example, in the state, for the state matrix A, the green components, which are the ones that we want to learn, represent agent-agent interactions. The off-diagonal component represent the agent dynamics, and those are not learned. We assume that we know them. As a result, the conditional variational autoencoder model produces a mixture of models corresponding to different latent behaviors. The end result is a model with a more structured output that we show leads to a very minimal loss in performance from the point of view of prediction accuracy, but dramatically simplifies downstream control, because of course, a linear time varying model can be used seamlessly in any model predicted control routine of your choice. So this dramatically decreases computation time to the point that before we were using GPUs for decision making. Now we can do everything and even better by just using a CPU implementation. I will conclude my talk with just a couple of pointers to two related research directions on this topic. First, we're working on how to account for uncertainty in trajectory forecasting that comes from upstream perception. For example, we're looking at propagating uncertainty all the way from the perception model all the way to trajectory forecasting. For example, uncertainty in the classification of an object as depicted in the picture on the left. And also how to make trajectory forecasting robust to perception noise. And finally, we're working on embedding logic in the model. For example, in order to be able to use as conditioning variables logic formulae that could represent, for example, rules of the road. Specifically, we use as logic formalism signal temporal logic, and we have recently devised a framework to translate the signal temporal logic formulae in the same graph computational paradigm that is used for deep learning. So basically, we can have speak the same language between symbolic reasoning, so signal temporal logic, and deep neural networks. And we're using the result in a couple of ways. One, we can jointly learn a model to optimize for prediction accuracy and robustness to a given logic formula, thereby embedding logical structure into a deep learning model. And second, we could also use this formalism in order to test for the correctness of a neural network model after training. With that, I would like to thank the two main contributors to this work, Karen Leung and Boris Ivanovic, and I'll be happy to take any questions you might have.
Thank you, Marco. Really cool stuff. There's a question here. Could you mention how safety was verified?
In what context?
Marco Carmona, I'm not sure exactly what context.
So if we talk about control, actually, so there's a much broader question. But basically, once we use these trajectory prediction models in order to inform decision making, we produce a plan that could be unsafe. The reason why it could be unsafe is that we are relying on probabilistic predictions about what the other human agents are going to do. So in order to gain some safety assurances, it is critical to augment the decision-making pipeline with a low-level controller that reasons more adversarially and enacts collision avoidance at a much higher frequency. How to glue the two is the real challenge. So we have a bunch of related work on how to properly glue a performance-centric decision-making module that is trying to promote efficiency and leverages probabilistic information with a lower-level controller that tries to promote safety by reason adversarially. And we have a bunch of work in this area that I'd be happy to discuss offline.
Excellent. Thanks a lot, Marco. I think with that, we can bring this session to a close. From my side, I would like to just thank the speakers from this session. I think it was really interesting all around. Thank you very much. And Dorsa, I'll let you close off.
Right. Yeah, I just wanted to thank everyone for coming together in this kind of difficult times in an online fashion. So I think it's been great, and I really hope we would be able to see you guys in person next year at Stanford or maybe Berkeley. Unclear. We'll discuss this with Mark. But yeah.
Maybe the cloud. Dorsa and I will have to have a fist fight about that, I think.
Yeah. All right. Thanks, everyone. This is the end of the program.
Just a reminder, we will still be active. I mean, you're welcome to remain active on the Slack, the students, etc. I think I'll also still be active on Slack for a while. So no need to abandon bars completely yet, but this will be the end of the stream.